go. Are you all set up here?
I think so, yeah.
Do you have any audio in your presentation? Do you have any audio in your presentation?
No.
Okay. Here's for you, and then this is for Q&A.
Yeah, I need to talk into the mic? Or?
Yes.
Okay.
The only way for you to be heard in the stream is to talk into the mic.
Yeah, I get it.
Anybody who asks questions also needs to speak into a mic to be heard. So the Q&A mic is here. Okay.
Should I start now? Or? Yeah, let's go. Like that? Okay. So, hello everyone and good morning after the keynote. My name is Oscar Laverny and I'm here to talk about an optimization problem that I stumbled upon in the middle of my thesis that actually forced me to use Julia. It was 2.5 years ago, and since then I kept using it, of course. It's one of the reasons that I'm here. But yeah, the point of the talk is to describe you the problem and explain to you why Julia was in fact the unique possible solution to this problem. So I'm going to start by describing the problem itself. I'll propose an algorithm to solve it, and then from this algorithm we'll discuss the whys and the hows of the need for Julia. So the problem is actually quite simple. There are a lot of equations on the screen, but it's not that complicated. There is a class of distributions, which is called the Thorin class of gamma convolutions, and which is simply defined by their cumulative generating function as follows. This class of distribution is actually representable as a risk factor structure on the bottom of the slide, and it's the distribution of the random vector x that is defined as a matrix vector product where the s's in the matrix are parameters and the g's are independent gamma random variable which all have shapes alphas that are also parameters. And so the problem is a parametric estimation problem, right? We have observations from the random vector x, and we want to find the set of parameters alpha and s's that corresponds to these observations. It's quite a classical problem. The issue is that we have no density. The model is defined in the complex space from its moment generating function m and its cumulative generating function k, which is simply the log of m. And when we started working on this class of distributions in 2020, there were no estimation procedure available. It's probably because of the deconvolution nature of the problem. In fact, it's a hard numerical problem. So the first thing that we proposed is to tackle the problem by using a loss that is a projection of the squared loss on the densities into a given orthonormal basis of L2 of R plus D. The basis is simply the Laga basis. This is the orthonormal basis that is associated to gamma distributions, so it's quite natural to use this one. I won't bother you a lot about the definition of the basis itself. But if the density of the random vector f is square integrable, then we can project it into the basis, and we obtain a set of coefficients AP that are simply defined as the integral of phi against the density. Which is explicited there. And so there is a bunch of combinatorial stuff here, and here there are things that are in fact the derivative of the moment generating function taken at a point -1. And this provides a loss, which is the approximation of the squared error between the true density and the estimated density from the data into the basis. So we are first to truncate the basis, of course. I won't bother you about the justification of the truncation, the exponential decaying of the coefficients and blah blah blah. But there are some coefficients AK hat that we estimate through Monte Carlo from the data. That's the easy part. And there are some coefficient AK of alpha s, which we need to compute from the parameters to be able to compute the loss and fit the parameters. This is the problematic part. To compute these coefficients, we have an algorithm that I won't describe you completely, but basically what it does is that it computes the derivative of the cumulative generating function, and then through a Faddeeville formula, the derivative of the moment generating function, the muse, and then through this combinatorial equation, it computes the Laga coefficients, and then it returns the loss in the bottom. This algorithm is pretty fast. That's actually, we can actually prove that it's the fastest possible, but it has a lot of flaws. So let's try to understand what are the flaws of this algorithm. The first one is that it's full of factorials and binomial coefficients. That's a huge problem because it will overflow. I promise you it will overflow. Yeah, there are basically factorials and binomials on every line, right? So that's a problem. The second problem is that it's fully recursive and each line depends on all the previous line. So it's completely linear. You cannot parallelize it at all. That's also problematic because it will require performance computations and probably compiled code to be able to achieve some kind of performance. And the last problem is that the loss that we produce is not convex, but not convex at all. It's actually a dense polynomial into some transformation of the parameters. It has a lot of local minimas, and what we want is the global minima, of course. But to found it, we need to use some heuristics and some global minimization routines, and this is also not a very good found, right? So, 3 problems. The first one is that the algorithm is full of combinatorial stuff, and so we probably require some arbitrary precision computations. The second one is that it's highly recursive. It cannot be parallelized, and therefore to avoid spending too much time, we probably need to compile stuff. And the third one is that it's highly non-convex, and so we require some global optimization routines. The arbitrary precision computation can be done in many languages, usually through a wrapper of the MPFR, which is the base one. The big floats in Julia are just a wrapper of the C MPFR. This is also available in R, in Python, in MATLAB, and in a lot of languages, so that's not a problem. The global optimization routines are also available in a lot of languages. There are particle swarms, for example, in Julia, in C++, in R. And compilation can also be done in a lot of languages through just-in-time compilations or even beforehand if you have a language that supports it. But global optimization routines that works in arbitrary precisions, that's something that is only available in Julia. That's something that doesn't exist everywhere else. Unless you recode the global optimization library to handle big floats, which will take 10 person and a year of work, which I don't have as a PhD. Unless you recode the arbitrary precision library, which will also take a lot of work, and I can't do that. And so I learned Julia. It was the easiest way to solve the problem. To give you some numbers, on a quite standard example for what I had to do, if I compute stuff in float 64, to compute the loss, it takes 0.12 of a second, but the error is of the order 10 to the hundreds, and so that's not very good. This is the combinatorial stuff that are producing basically noise, and so we are trying to minimize noise, which is not very useful. And we have to go down and to increase the precision. If we go to big float, which is 256 digits of precision, in base 2, I think. We got the correct loss, which is of the order 10 to the minus 8. And in fact, if we go into multi-floats, we need to go to 5 times the precision of float 64 to have the correct loss and to be able to work and actually to minimize what we want to do. And voila, this thing has been the subject of a discourse thread 2 years ago that is still there, and on which we discussed a lot about what will be the right implementation. And there is also a final code on some package that is not registered at all. It's just I stored it there because I needed to keep it somewhere. Voila, thank you very much. If you have questions, I'm over here. Yeah.
Use the microphone if you have questions.
Oh.
Thank you. So probably naive question, but whenever I run into the combinatorial stuff and the factorials, I log transform it, and I can work with float 64s and things like that for my use cases. I assume maybe that's not feasible here.
Yes, it's not. It's not feasible because what we have, maybe it's, yeah, on this one. What we have basically is we already log transformed it. The log transformation is the fact that we compute the kappas there, which are the derivative of the log. And then to unlog transform it, we have to apply the Fadibolo formula to get the derivative of the exponential of k, to get the derivative of m. And this is the combinatorial stuff. So it's already what we did, but to get back from it, you still need to apply some combinatorial mechanisms. Okay, so thank you.
Hello? Hello? Yeah, can you hear me? Hello everyone, it's a pleasure to be at JuliaCon. Welcome to the presentation of Airfoil GMSH. Yeah, my name is Carlo Brunelli. I work as a researcher at the Royal Military Academy. I also come from Belgium. And I'm here today to show you how to use this package and which are his features. I started developing this quite simple and small package because I'm dealing constantly with Airfoil, and as may suppose also other researchers and engineers are dealing with Airfoil and meshes, and it's a tedious sequence of operation to create a mesh for an Airfoil, and that you have to repeat over and over. For who doesn't know, GMSH is a free open source software for mesh creation, and it can read geo file. And the aim of the package is to create the geo file that can be read directly into GMSH. And this is, for example, a geo file which has been read, which has been created using Airfoil, the package, Airfoil GMSH. And this is the geo file, which is read. And in GMSH, we can see a domain like this. At the center, we have our Airfoil, and a typical domain for studying Airfoil in free flow conditions. And the creation of a structured mesh, it's a mere click here on the left. And we can see that we have a fully, we have a mesh, a 2D mesh, which is fully parameterized. So it means that on the panel here on the left, I organized the geo file in order to make the mesh fully parametric. So for example, we can modify the angle of attack, and here the Airfoil rotates, and we can immediately recreate a new mesh. It's also possible to change the whole domain dimension. For example, on the back, we can extend or reduce the front or the back of our domain and remesh again. Or also all the divisions inside the domain. For example, at the top part of the Airfoil, we can reduce the number of division and remesh immediately. So you can see that it's really easy to use. And yeah, that was the demo that I want to show you. Let's go back to the presentation. So the package has been realized to automatize to have an automatization of the creation of structured meshes. And you will see that it's possible to, in few lines of Julia code, to create a geo file to be read in Airfoil GMSH. It avoids routine operation. It has been decided to create a geo file instead of a classic .msh file because it's much more human readable, compact, and for a quite expert user, it's also easier to have a custom modification of it. The features which are currently implemented, it's possible to create a quadrangular or a triangular mesh, element meshes. It automatically recognizes if the trailing edge is sharp or not sharp, and the mesh is created as a consequence. It's possible to create also a 3D mesh, and with a simple command, and This is a geofile with a 3D mesh, and it's created pretty fast. All over all the boundaries, inlet, outlet, over the airfoil and the limits are automatically added the tag. So once you export the mesh and you import the mesh in your code, finite element code or finite volume, they are automatically recognized. It's possible to create an airfoil directly browsing on airfoiltools.com, which is a database containing tons of airfoils. You can just copy-paste the URL, and you immediately can have your airfoil. It supports a boundary layer analysis for your viscous simulation, and there is also the support for class shape transformation. Here is just, there are a couple of examples on how you can use the package. It's a registered package, and so you call airfoil GMSH. You can copy the URL obtained surfing on Airfoil tools, and you can create a CSV file with the function here from URL to CSV, and using this CSV or another CSV that has been provided, for example, from optimization simulation or some other study, you can create the geofile in basically just one line. The option that you can set, you can choose to create a 2D or a 3D mesh, the type of the element, and the user can also specify their Reynolds number. If the Reynolds number is specified, then it's triggered a boundary layer analysis where there are some empirical formulas, and the code is estimating the total boundary layer thickness and also the maximum height of the first layer to capture all the flow features around the airfoil. There is a small optimization process and cycle where the code is looking for having at least 30 cells inside the boundary layer and a growth ratio between 1.1 and also 1.2. Finally, it has been added also the support to class shape transformation, which are mathematical means and formulation which are used to describe airfoils. Sometimes they are defined in a not enough number of points, so they have a low resolution, and so we want to increase the resolution of the airfoil. In fact, if we use not enough points for creating our mesh, we can also obtain a not really well-defined mesh, a low coarse mesh, not really suitable for our cases. So we can have an airfoil which is better resolved with a better resolution using a class shape transformation. So in this case, we load our CSV file where there are not enough points. We can say, for example, in this case, that we want our airfoil to be defined over 500 points, and we can have a better airfoil and hopefully also a better mesh. So in conclusion, here there is just a sum up of the workflow that I suggest you to follow if you want to use and try this package. I hope this can save you some time if you are working with Airfoil as I do, and thanks for your attention.
Can you maybe say one or two words about your larger flow from picking an airfoil to how you simulate it in practice? Sort of short example how the whole flow of using this works in a larger.
For example, for my studies, I'm trying to I have to test different airfoils to find which are the most suitable for our flow condition. For example, I'm studying low Reynolds airfoil, so I had to test different airfoils. So it was a tedious routine to me every time to look a new airfoil, creating the whole domain and so on. And this, for me, speeded up the procedure. And once I have the mesh, that for me it's fine from GMSH, I can just export the MSH file, and I'm developing a finite a solver using finite element method, and which is using a library called GridUp, which is completely written in Julia. And I'm implementing a variational multiscale method to solve these kind of flows, but probably this will be the talk for next year.
Thank you.
okay?
Hello, can you hear me well? Okay. Good morning, everyone. So I am Kun Chen. I'm from Flatiron Institute, and in this talk, I would like to talk about a package we recently developed. It's called mcintegration.jl, and it's a native Julia package dedicated for high-dimensional numerical integration problem. Why we developed this package? Well, this is because the high-dimensional numerical integration is really one of the fundamental components of numerical science. So this kind of problem pops out like in almost all different kinds of fields. So for example, physics, data science, finance, machine learning, and so on. And this kind of problem is typically very difficult to solve once the dimension is higher than 3. So the reason is because there is a curse of dimensionality if you use a uniform mesh, uniform grid system to estimate the integral. And you can show that if you want to achieve epsilon accuracy, like the grid points you need, it will be exponentially increased with dimensions. Okay, so to overcome this problem, people invented the Monte Carlo technique, and the overall idea is very simple. So, for example, if you want to estimate the pi, which will be the area of the unit circle, what you need to do is just draw a bunch of random points in a square and count how many points are within the circle. And this simple approach turns out to have a very nice feature. So what it turns out is that if you want to achieve accuracy epsilon, the data points you need doesn't scale with the dimension. So that makes it a very promising tool to solve the high-dimensional integral problem. So we use the native Julia to implement a package to solve a generic problem like that. And thanks to the Julia's language feature, our package achieves both performance and flexibility at the same time. And we also implemented a couple of state-of-the-art algorithms to make sure the package is efficient and robust for generic high-dimensional integral problems. And we take parallelization seriously, so we support both MPI and multi-threading parallelization. And with this package, you can solve many problems like integration and solve like integral equations, measure histogram, sample distributions, and so on. And the usage of the package is quite simple. So you just need to define your integrand and call the integrate function to calculate the integral. And there will be no problem even if your function contains a singularity. And then why we choose Julia to implement this package? Well, this is because in the field of numerical integration, there is a battle between speed and efficiency. And Julia promised to solve this two-language problem. So to do a numerical integration, basically what you need to do is you need to write down a user-defined integrand, and then use the package to evaluate your integrand for like a million or billions of times. Okay, so there are two costs: human labor cost to implement the integrand, and there are computation costs to actually evaluate this. And both are very important. So for all packages existing in the market, they either focus on the performance, speed, or they focus on the flexibility. And thanks to the feature of Julia, we can kill two birds with one stone. And we did a benchmark, basically by evaluating dozens of integrals and we find the performance of our package can compete with a similar package in C without sacrificing flexibility. Okay, so in our package, to make sure like we can efficiently sample the integrals, we use a technique called the Vegas map, originally invented by Lapage in 1970s. And the overall idea can be illustrated with a simple example, which is a three-dimensional integral. And the integrand, this integrand actually develops a singular behavior at the corners of the parameter space. So it's actually very difficult to calculate. And naively, you will say to have a good performance, instead of randomly put data points, you need to sample these singular points more frequently. And the Vegas map is precisely doing that in a very efficient way. So what we find is that with this simple, example, Vegas map can boost your efficiency by a factor of 1,000. And in addition to the Vegas map, we use another important sampling technique to make the calculation very robust, even if there are like 100 or 1,000 dimensions. And this is because, and this technique is a Monte Carlo algorithm. And this is because Vegas map can fail if the dimension is extremely high. For example, if you generalize the pi estimation example to d dimension. And then what it turns out is that the difficulty, like factorial increases. So to sample the 100-dimension problem, you have to sample 10 to the power 70 points. Then you can hit the hypersphere. Okay, so the integration becomes very difficult, and the Vegas map here cannot help us anymore. So in addition to the on top of the Vegas map, basically we implement a Monte Carlo algorithm to directly sample the distribution, which is proportional to the integrand. And with this additional layer of algorithm, now actually we can handle like more than 100 dimensions without a problem. Where on the other hand, the traditional conventional algorithm stop working roughly at 10. Then with this, in the end of my talk, like I would like to give you one real-world example, how to solve, basically how to use this package to understand why our sun shine. Okay, so we know that nowadays we all know that what powers our sun is basically the proton-proton nuclear fusion. But back in 1920s, people have trouble to understand how this could be possible. The reason is because there are strong Coulomb repulsion between proton-proton particles, and this Coulomb barrier like prevent the protons get closer enough to. So at that time, people trying to understand how they can get closer enough to trigger the nuclear fusion. So then it turns out what helps you here is a phenomenon called quantum tunneling. So it turns out there are always a small probability that the protons get closer enough at a short period of time, and they are close enough to trigger the nuclear fusion. And then at this short period of time, the proton will form like a resonant state, and the resonant dynamics is described by a quantity called the T matrix. And to calculate the short-time behavior of the T matrix, you need to solve this integral equation. Okay, so it's actually quite a difficult equation to solve because it involves the integration here, and it's self-consistent, and it also contains a singular. This integrand is singular in short at 0 time. And then you can use our package to solve this problem. The thing you need to do is you start with the initial guess of the T matrix and use the package to calculate this integrand in both parameters tau and t. And then you measure the histogram of this integrand as a function of t. And this histogram gives you the next iteration of the t matrix. And then you just run this iteration again and again. Eventually, you will find the t matrix is highly non-trivial. So it's actually power law behavior at a short time, and it actually diverges at a 0 time. So this, it's not zero. So this is precisely the feature of a resonance state. So if you work out this problem like 100 years ago, actually you have a chance to get a Nobel Prize. Okay. So our package is actually developed on the umbrella of a NEFT project. So this is a project to develop a modern effective field theory framework to solve quantum material problems. And MC integration is a key part of it. So basically now we use this package to calculate the high order Feynman diagrams for different problems. Okay, so in the end, I would like to thank the developers and the maintainers of the Cuba package and the Cuba.jl package and the Vegas package. So we learned a lot from them, and we got many new ideas from them. And I also would like to thank the contributors, Xiansheng Cai, Pengcheng Hou, and Daniel Sacroni. Okay, so that will be the summary of my talk. Thank you very much. Okay. Any questions? Yeah. Okay. Thank you very much.
Did you compare it with MVT norm and things like that? Sorry, MVT norm? In R.
In R. Oh.
MVT norm. But I think that is also Monte Carlo.
I see. I don't have much experience with R.
I think
Testing 1, 2, 3. Working on it. We good? All set? Okay. Well, good morning, everyone. I'm Sam. I'm a computational physicist at the University of Rochester, and I'll be talking to you today about simulating inertial confinement fusion physics in Julia. So the package that I wrote is called Cygnus. It's recently developed multi-physics code that we're using to study physics relevant to inertial confinement fusion, often called ICF. Simulating ICF experiments is a significant challenge, even in 2D, due to the multi-physics nature of implosions. So we have shocks, thermal conduction, radiation transport, and a whole host of different physical processes. Typically, these ICF simulations are done in large-scale codes written in Fortran or C++. And here we have Lawrence Livermore lab uses Hydra. Our lab uses Draco. Los Alamos has X-Rage. And then there's also Flash, which is a pretty common astrophysics code. And Julia, as we all know here, offers a compelling alternative that combines performance and productivity. And so Cygnus has been serving kind of as an extensible library to experiment with algorithm development and multi-physics code design. The end goal is a full-fledged HPC code to study relevant physics for ICF implosions. I'd like to thank my collaborators, some scientists at the University of Rochester, and a grad student that's working with me. So we'll go over a brief introduction to inertial confinement fusion. I'll mostly work with pictures here. So there are two main approaches to ICF. We have direct and indirect drive. On the right, we see indirect drive, where we have a whole ROM, which is a gold can, you'll see here, and they shoot laser beams into the edges, into the holes on either side. And what this does is it creates, it essentially ablates the gold on the inside, creates X-rays, and drives our little target in the middle inward. In direct drive, there is no whole ROM. Instead, we just shoot the capsule directly. The idea is to drive the capsule and implode it. So ICF implosions compress spherical targets filled with deuterium and tritium fuel in 4 distinct phases. So in the first phase, we have uniform illumination. So here, if we think about the direct drive case, your lasers directly illuminate the outside of your target. This is a plastic sphere. So you have the plastic melting on the outside. It drives this capsule inward like a rocket. The next stage would be compression. Here you have the shell continuing to move inwards, and you have a corona that starts to form on the outside. This is a plasma now. Then we have ignition, where the center of the target gets hot enough and dense enough to actually create fusion. And then once that ignites, then we burn, and we release all sorts of energy. So the Laboratory for Laser Energetics is a Department of Energy and NNSA-funded lab at the University of Rochester that studies direct drive ICF. There's approximately 400 scientists and staff with about 100 students in all levels, including high school students, all the way up to PhD students. Shown here in the top right, we have Omega is the name of our laser system. We have 2 different laser systems. Our primary one is here. It's called Omega. There are 60 laser beams that symmetrically illuminate a target at the center of a target chamber. And on the left here, we have Omega EP, which is a short pulse laser, which we use for other focused experiments. If you want to study laser fusion, lasers, or higher energy density physics, this is a place to come. So if you're curious, I would recommend checking out the link here. So Cygnus, this Julia package, is being used to study the impact of defects commonly found in these targets. Here, this is a schematic of a typical target that we shoot. This is a sphere, so the outermost layer is plastic, carbon and hydrogen. And then on the inside, we fill it with deuterium and tritium, and we freeze it so that it forms a layer of ice on the inside. And then we have a region in the middle that is vapor. And the diameter is approximately 1 millimeter, just to give you a sense of scale. Some of the things we have to worry about, there is ice inner surface roughness. We have gaps between these interfaces. We have defects on the outside, like surface domes. We have bubbles inside the ice, and we also have defects inside the shell. So this is an example of a shell that has been cut apart, and you can see a slight defect on the inside. And the reason these are important is because they cause our implosions to become less uniform. So anything that's wrong with the target will get amplified and degrade any potential yield at the end. So one of the things we can do is we run high-resolution axisymmetric wedges to determine performance degradation prior to peak compression. So what all this means is we don't simulate the whole thing all at once in this case. And we just focus on a particular region. So we'll look at this section here. And then on the right here, this is an example of a simulation domain. So here we have a layer of plastic on the outside, a layer of ice, and then gas on the inside. And on the right here, this is just vacuum. So there is a tiny surface dome here for scale, just to give you a sense of how big these things are. So, you know, they're very tiny. They're only about a micron high, but you wouldn't think they'd have a big impact, but they do. Because this is axisymmetric, we assume an axis of rotation or symmetry. So this is run in 2D. And we need sub-micron resolution to track shocks and waves created by this defect. So here's an example. We zoom in, and we have a slight defect here. And if we advance further in time, we see that when the laser hits the outside of the target, it launches a shock wave. And we start to see this is the defect and all the perturbation that's created by this. So I'll show a movie here in a second. So the color of these pictures is indicating the density of a particular material. So we'll go ahead. Again, here's a result from a simulation. We have a defect here. This is a plastic layer, a layer of ice, and gas on the inside. And the laser beam, it will be coming in from the right. It will melt the plastic and drive a shock inward. We can see multiple shock waves, and then obviously the impact caused by the defect. So what is happening here is we have, this would be the dense shell, and we see all sorts of instabilities form because of this tiny defect. And it ends up later on in the implosion, when we get to where we want to compress the gas in the middle, we have holes that form, and we no longer get ideal compression. So this is a bad thing. Simulating these is a significant challenge, even in 2D. Some of the relevant physics, including multi-material hydrodynamics, so we can capture shock waves, material interfaces, instabilities, like Rayleigh-Taylor and Richtmeier-Meshkov. Thermal conduction for laser ablation. Laser light propagation, how we deposit the energy. Ionization and radiation, so the coronal and core emission. Particle transport, we have alpha particles and neutron scattering. Complex equations of state, this is relating pressure, temperature, and density, and much more. But the nice thing is we can still produce valuable research without adding every possible physics process thrown in. So we can just use a small subset, and this is where Cygnus comes in. So Cygnus is a new high-order multi-physics code for targeting physics studies relevant to ICF. And at a first go, we have high-order fluid dynamics. We're solving the Euler equations. It currently is for a single material, single temperature. It uses the finite volume method with arbitrary 1D or 2D block-structured grids. It uses a couple different Riemann solvers. If you're not familiar with those, don't worry about it. It's just a way of solving these equations. And then we have multiple orders in space, second, third, and fifth, and then third order in time for Runge-Kutta. For thermal conduction, we assume Spitzer conductivity. We use an implicit solver. There's two different methods. We use a backward in time, central in space, or we have the alternate direction implicit solver for 1D and 2D. And then there is a semi-implicit 2D solver under development, and this is designed to run either on the CPU or GPU. Right now, we assume an ideal gas equation of state, but tabular EOSs are on the roadmap. So here, when you have complex materials like aluminum or plastic or gold, we need to look up from a table how this material interacts, as opposed to just using the perfect gas law. The laser is currently mimicked using an energy deposition source term. This is kind of a hack, but the way to do it precisely, according to physics, is to use ray tracing, and this is something that's currently under development. And then for the coupling between these different physics packages, we use Strang operator splitting. This is essentially just a divide and conquer approach. So the idea here is that we want to use Cygnus as a library. and add additional physics with new modules or types by users or new developers. So the hydro and thermal conduction modules have different requirements and parallelization strategies. So for the hydro, we use a block-based shared memory threading. This is a simple approach where you just divide your domain up into blocks, and you have halo regions in between where you exchange data in between each time step. This is a simple to map to MPI. Right now it's shared memory, but you can move to MPI for domain decomposition. For the thermal conduction solver, this is a diffusion approach. The primary mode is an alternating direction implicit split method. So here we do threaded sweeps across. First you do across column, and then you do row, and you can switch back and forth between what order you're doing it. And so here we are just solving a tri-diagonal system of equations for each row and column, and you can thread across that. Efforts so far have been to improve on-node performance, but the planned model is to use 1 or 2 MPI ranks per node and then do threading from there on. Domain decomposition will be provided by the MPI Halo Arrays.jl library. This is a registered package that I wrote about a year ago, and the basic goal of this is to make it easy to do halo exchanges for arrays of arbitrary size. And you can do this 1D, 2D, or 3D parallel topologies. Right now it's restricted to Cartesian, but you can choose arbitrary halo sizes depending on the order of your solver. So here in the picture we show for 1D with a halo region of 3 cells. You can see that here in gray. And when you're syncing the halos between 2 different domains or 2 different processors, you do an exchange, and this library makes it very simple. So here's a pseudocode. You can look online to see the details, but essentially you have to create a topology first to tell the code what the decomposition is. So here we're splitting the domain up in 2D, 4x4, and we're going to use periodic boundary conditions in both dimensions. And you specify how many halo cells. This is fixed for all the domains. It can be anything from 0 to n. And then down here we're just creating a simple halo array, 200 by 200, and you pass it the size of the topology and the halo. Then you do all sorts of complicated things. When you do accesses, it's like a normal array, and it will be computing this. This is an indexing on the current rank in an MPI setting, and then whenever you want to do the halo exchange, you just call the update halo, and it will do this for you. Laser ray tracing is currently under development and should be added in the next few months. The interesting thing about ray tracing in a plasma physics setting is that it's not like computer graphics, where we don't have an accelerated bounding volume hierarchy to go through. Rays have to propagate through the mesh 1 cell at a time. And they have curved trajectories. This is defined by a density gradient, electron density gradient. So here, in the picture here, I show there's a linear density gradient in the heat map. So it's increasing as you go to the right. And it forms something called a critical density. This is where laser light cannot propagate past a particular density of electrons. And it causes these rays to refract and curve. And so here, you've got rays that are entering the domain in the lower corner, and they're colored by the cell. So it gets a new color as it moves through a particular cell. And depending on the velocity vector of these particular rays, you get different trajectories that curve. And as it does that, it deposits energy into your mesh. And this is how you get a source term that drives your particular problem. The tricky part here is parallelization. Do you do domain decomposition or duplication? Primarily, you do it threading on a particular node, and then you communicate with your surrounding nodes. So this is a work in progress. Optimizing on-node performance of existing physics models has been the primary focus so far. So we're working on a semi-implicit model for a diffusion solver. This does thermal conduction and eventually also does radiation. But this will use the same data layout as the hydro, and this is favorable for GPUs as well. The parallelization strategies for hydro, the data layout, I've tried a couple different approaches. One is splitting it up into blocks, and one is using single arrays and threading over that. And I'll go over some of the different types that I've used. So thus far, the hydrodynamics portion takes about 60 to 70% of the total runtime. And how do we optimize this? And so one of the issues here is that finite volume methods are inherently memory bound. So we're going to go over finite volume in a nutshell. You get a crash course on how you do finite volume. So it's a robust method to simulate complex fluid flow in arbitrary geometry. So the picture I'm showing here is an example from an integrated test that does the Kelvin-Helmholtz fluid instability. So you have a shear layer form. You have velocity going to the left in the center and to the right on the top and bottom, and you have some sort of sinusoidal perturbation that causes this roll-up to happen. And we're coloring it by density. But the main point is if we zoom in, we see that it's defined on a grid. And we zoom in even more, and we have a quadrilateral of arbitrary size. So in the finite volume method, you have, this is a quadrilateral, you have normal vectors that define the edges, and you store your state at the cell center. And when you do this for an unsteady problem, you want to see how this state in the middle, in the cell center, changes versus time. You need to know the fluxes of material across the edges, and you need to know if there's any source terms defined in the middle. So we advance in time by using a multi-stage Runge-Kutta algorithm. This is pretty common. This is a third order version. We're going to advance from time step n to n plus 1. So there's 3 stages. The first stage we show here, second stage, third stage. The point is, without getting tied up in all the math, we have to figure out the derivative du dt 3 times. And how do we do that? Well, I just showed a really basic, we'll walk through it a little bit. So as we integrate, so here's we have a type that defines your Runge-Kutta struct. And we want to integrate it in time, and we're just doing a simple loop over all of the indices in the domain. And then we call this du dt function, and we do this 3 times. In between, we have to do a halo update where we exchange data with our neighbors. So first, we store the fluid state at the cell centers. And so that's what U stands for here. We're just storing pressure, density, velocity at the cell center. A lot of times you might see, if you're familiar with this, you can work with either conserved or primitive variables. It doesn't really, for this talk, it doesn't really make a difference. But the point is we're storing it at the cell center. Next, we have to figure out what the value is at the edge, because ultimately we want to find out the flux of material that goes across the edge. And we do this via higher order methods, and we get when we reconstruct it, we use a stencil similar to this one here. We ultimately want to find the value at the square, but we need the values at the circles to do so. And when we reconstruct it, we get what we call a left and right state. So we have left on this side and right on this side. And if common methods include muscle or Wino. And here, in terms of Julia, it's just passing it the cell-centered values in a particular stencil like this. Then we have to compute the flux of material across the edges. This is just calling a Riemann solver. So here's the math version and the Julia version. We just pass it the state on the left and the right side of the edge, and then we give it a Riemann solver. So here, these are different types of solvers that you can do, but in terms of the function, it doesn't matter. So these Riemann solvers take flow characteristics into account, things such as subsonic or supersonic flow, rarefaction waves. But the point here is that these are not traditionally flop intensive. They're more memory bound. And the final stage that we need to do is we have to sum up the contribution from all of the edges. So we just got the fluxes, the F values for each edge. We sum them up and divide by the volume. Now we know how the state changes in time, or du dt, and this is what we use inside the multi-stage Runge-Kutta scheme. The important thing to note here is that this is a cell-centered quantity, but the flux values are edge-based. And why does this matter? It matters because of memory access. So I've tried 3 different approaches so far. We have simple multi-threaded loops, block-based task spawning, and then we have what's called a local stencil approach. The issues with the first 2 is they're memory bound because we have to use intermediate storage arrays to store data along the edges. In the local stencil approach, we create a new type and compute the entire cell at once as opposed to looping through and doing things for each edge. So the first approach is pretty simple. We just use a loop vectorization macro at t-turbo, and we have a nice fast parallel loop. And we do this, so this is one of the stages. And this works pretty easily, but it doesn't always scale well because of memory access. So the next strategy was to do it with tasks and blocks. So each task we do, we spawn a new thread, but it still uses intermediate arrays to store edge data. So this primarily required a new array type, block halo array. These are NUMA aware allocated. And in terms of adjustments to the code, it was pretty simple, just a little bit more cumbersome due to having to know which block you're in. And here's some pseudocode. You basically loop over the number of blocks and you spawn a new thread for that particular block. And inside that, you just call the 4 different tasks that you need to do to solve the problem. The final version moved to a local stencil type. The emphasis here is that we only want to read from the global data once. So we create a stencil for each cell, advance the solution, and then parallelize across cell indices. This eliminates intermediate arrays, and this is an attempt to reduce the dependency of memory bandwidth. But here's the kicker. This method actually duplicates work, but it ends up being faster because in this method, all 4 edges are computed in one pass. In algorithms 1 and 2, edge data is shared, so cells only have to compute 2 edges. So it's kind of counterintuitive, but we end up with a faster algorithm when we stick everything in a new struct. So the stencil type contains all the data required to advance the solution forward in time for a single cell. Here we stick the data in basically a S matrix with S vectors. There's a few other terms here, but the idea is that we want everything to be static so that the compiler can optimize. And we do threading across cell indices. So here, obtaining peak performance depended critically on using the @batch macro and the underlying pointer arrays that it casts everything to. So again, here we're just looping over the cell indices and parallelizing this way. And this particular function computes everything we need. Strong scaling benchmarks show improved performance for the local stencil method. So this is a fully integrated test where we're doing a blast wave. So you just think of a square domain. You dump a bunch of energy in the middle and it just creates a blast wave. About 4 million cells, and the timing here I'm showing is only from the hydrodynamics portion. So the machine I ran this on has 16 cores. Once you go above the number of cores, if you're trying to use hyperthreading, you're not going to get any advantage. So the old algorithm was block-based here. We see the scaling tend to fall off a little bit. The idea here is obviously you want the ideal where you add 2 cores, you get a 2x speed up. And this local stencil method, we get about 98.5% parallel efficiency, which normally when you see these strong scaling slides, they'll do it on a log-log scale to hide the fact that they're not quite ideal. So I was pretty happy. We can also look at this using an empirical roofline model. And the idea here is you want to characterize how well your algorithm is utilizing the machine that you're on. So first step is to know what your machine can do. So I use the empirical roofline toolkit from Berkeley Labs. This will run a suite of benchmarks and give you some bandwidth and floating point operation numbers for your machine. So here, each roofline tells you the memory bandwidth of your hierarchy of memory. So you have DRAM, your L3, L2, and L1 cache. And if you're on this side of the dashed line here, it means you're limited by bandwidth. And if you're on this side, it means you're limited by floating point operations. So an optimized approach is as close to the roof of your particular memory hierarchy as possible. So in the new method, we are above DRAM, which means that we are benefiting from some cache reuse, which is good for scaling. So I'm at my time limit, so I will end it there, but thank you for your time. Next.
Okay, thank you everyone for being here. My name is Henrik, and today is my great pleasure to be here to talk to you about how we can use Julia to optimize trajectories for robots with legs. So first I'd like to get started with a bit about my background, and so I can give you a bit of context on the work that I've been doing. And I'm originally from Portugal, where I did my undergrads and my bachelor's and my master's in computer science. And then I had the opportunity to go to the University of Edinburgh as an exchange student, and that's where I took my first course in robotics. And you can see here on figure number 1, the final project for this course, which was like a robot like put together with Legos and other off-the-shelf like bits and bobs of electronics, and you had to go around the maze picking up cubes with specific images. It was really nice, and it really got me hooked into robotics, so much so I ended up staying for like other 4 to 5 years doing a PhD and postdoc there. So yeah, that happened. And that's where I stayed for until 2022. And more recently, I switched from academia to industry. And currently, I'm a robotics engineer at a company called Ocado in London, where we do autonomous pick and placing of groceries. So it's a company, it's mostly known for being an online supermarket, and you order your groceries, and then the warehouse is almost fully autonomous, and there's like these robots on wheels that move boxes of groceries around, and then there's these robot arms either with suction cups or grippers that pick and place the groceries from those boxes to the customer bags and then deliver them to the customer's home. So they were very kind in sponsoring part of my trip here by paying for my flights, so thank you very much for that. But today I'm here to talk to you about how I've used Julia for optimizing trajectories for robots with legs. So those are the robots that you can see here on figures number 2 and 3. In the beginning of my PhD, one of the first research projects that I started to work for was with this amazing piece of technology, like the robot on figure number 2. And this is a humanoid robot called Valkyrie, and it's made at NASA Johnson Space Center. And it's 130 kilos, and it stands at 1.80 meters tall. And it's very complicated, and it's very nice when it works, and very frustrating when it breaks. At the time, what I was doing is like planning the whole body configuration. So what that means is I was trying to find the joint values for like all the joints on the robot to be able to reach out for things, grasp bottles, and to also select carefully the foot placement on complicated terrain. But you know, like at this point I was using C++ and Python, and Boston Dynamics kept publishing all these crazy videos of robots doing backflips and jumps, and I really wanted to like start looking into more transitioning from planning whole body configurations, like a single whole body configuration, and switching to more planning agile motions and dynamic motions. So it turns out that if you want to optimize these kind of problems for robotics, the constraints are quite involved. And if you want to do research like I was trying to do about like trying different cost functions and changing cost terms, I was like doing very quick prototyping, and I was using finite differences at the time. So it was really, really slow and really painful. And I thought there must be a better way. And that's when I learned about automatic differentiation. And since I was using Python and C++, I was looking for alternatives. And I'm not sure if that has changed over the last few years, but when I was trying it, it was a huge pain as well. Like, I remember that I tried a Python library for autodiff, and it had like lots of constraints on how you were able to write the code. So, for example, if you had a for loop, you had to unroll the for loop. If you couldn't have if statements. And then C++ was also very verbose. And like I was finding myself in this situation where I was thinking about robotics problems, which were not necessarily very easy to think about. And then instead of having a language that was helping me get those problems across, I was having to fight Python and C++, which like, it's really not what I wanted to do. And so that's, I was almost ready to give up and to try a whole different topic altogether. But I decided to give a few more quick Google searches, and I found Julia. And I mean, I'm pretty sure that you all went through this stage. You found a mention to Julia about like these auto differentiation capabilities, forward diff, the performance promises, like all the nice packages. It was really too good to be true, or was it? And then I decided to give it a try. I started using the Julia language and the packages in the Julia ecosystem for a few different toy problems. And it was amazing, and it really worked. And like this problem that I was having about having to fight the language, when I was using Julia, I found that it was so easy to get the ideas across and just to prototype quickly. So, in summary, I think I switched for the autodiff, and I stayed for the rest. I guess that sums it up quite well. So, let's start with the robot demo, and try to get a bit of your attention on the nice video. Is it? Okay. So, this is the final demonstration video of one of the projects that I probably like the most during my time at Edinburgh, and it was like at the end of my stay there. And it's also this was for an European research project for offshore platforms and renewable energies. And so this is in the lab. It's a mock-up environment. You see the scaffolding. It's all normal scaffolding that we put together. And you can see a few different objects that the robot can interact with. You can see a wheel. You can see the lever. And you can notice that like on the bottom of the video, there's a few labels that keep switching. And so currently, the robot is walking. And you see that the operation mode is in teleoperated. And what this means is just that in my hand, I have like a remote controller, like a gamepad controller, and I'm just pushing the joysticks in the direction I want the robot to walk to. And this is a functionality that it's available off the shelf when you purchase like the quadruped from this company. By the way, it's called Animal Quadruped from Robotics in Switzerland. However, you notice here when it, for example, when it reaches this door or this gate, it changes into autonomous mode. And this is because it's really hard to teleoperate robots to do these kind of complex motions. And you can see that the whole body moves in a coordinated fashion. So the arm and the quadruped. And I should also add that the arm is made by a different company. And it's running a different controller. And these were not designed like to be put together. We just like put them together. And the trajectory optimization is considering the robot as a whole. But that you cannot buy off the shelf, you know. You have to do it. And so that's what I want to say is that the autonomous mode that you see here is Julia. Everything being planned, the motion planning is in Julia. Here, this task is particularly interesting because there's a bucket with a rope, and the robot needs to pull the rope to lift the bucket to a specific height. But just using the arm is not enough. So you're going to see it's taking steps at the same time as it pulls the rope by moving the arm. And these are very complicated problems in robotics. It may not seem like much, but it's a lot of work to get this to work on the real robot. Because you have like all these contact interaction, the breaking and making of contacts, and the external disturbances and the forces going on. So it's really, really interesting to look at this problem from a research perspective. So let's see how we can plan these kind of motions, the ones that I showed in autonomous mode. Let's see how we can do this using Julia. And but first, I want to give a quick introduction on what trajectory optimization is. And I'm not sure. I mean, I know there's a few people from robotics in the crowd, but I'm not sure if everyone knows the basics. So I'll just quickly go through it. There are two robots here on the right. There's a robot arm, and then there's a quadruped robot. They have a few similarities, but a few differences as well. The robot arm here has 6 moving joints, each of which with an actuator. And so to represent the state of this robot, which is the X over there, you can represent it using a 12-dimensional vector, the 6 positions and the 6 velocities at the current time, okay? And this is called a fully actuated system because there's a motor on every joint, and so we can directly change the state of the robot by moving the joints, by commanding currents or torques to the joints. However, in contrast, the quadruped, it's an under-actuated robot. And there's a nice course taught here at MIT by Professor Russ Tedrick on under-actuated robotics. And the main difference is that the quadruped is not fixed. It's not screwed on a table, or it's not bolted onto the wall. It can move around. And it does have motors on the legs, but it does not have a motor on its torso. So if the quadruped robot is standing on this corner of the room, and I want to move the robot to that corner of the room, there's no magical motor that I can just actuate to just magically move it there, or there's no jetpack to make the robot fly there. So what you end up having to do is you need to find the correct motion, so that the torques that you need to send to the motors on the legs to somehow move the robot there, either by jumping, by walking, by running, whatever. And so that's the main difference. And then there's also the contact force interaction at the feet, which needs to be handled properly. So in summary, for trajectory optimization, we need to be able to quantify state, controls, the dynamics of the system. The state, as I said, are the joint positions and the joint velocities concatenated. And for the quadruped, this includes the additional coordinates for the position and for the orientation of the torso, which is like the origin of the robot. And then what are the controls? Well, the controls that can change the state of the robot are the torques that we can apply at each of the motors and the contact forces that are exerted on the system. So these would be, for example, when the robot is the feet are on the ground, these will be the contact forces that the robot experiences from the contact interaction. So how are these related? These are related by the very famous equations of motion, which is that equation there on the bottom left. And I'm going to gloss a bit over the details, but essentially what they show is the relationship between the state and the control. So how do the controls affect the state? And they can give us the answer to questions like, if my robot is at a specific state right now, and I want the joints to accelerate in a certain way to reach another state, it can give us the torques that I need to apply at the motors to achieve that acceleration. Or we can look at the problem in the opposite way. So say if we're writing a simulator and we have the robot in a specific state, and I know the torques that I'm going to apply, we can use this equation to compute the joint accelerations that are a consequence of applying those torques. And so that, I think, summarizes pretty much the state, controls, and dynamics. And any questions up until this point? Yes?
So
okay, this I'm going to talk about next. Yeah. Yes. So this gives us the basic building blocks, okay, to describe the state and the controls to the system. But now we are going to get into the trajectory optimization problem, which is the interesting bit where we can start adding constraints on what the robot should do. So what's a trajectory optimization problem? Essentially, we have an initial state, that the state where the robot is currently. We have a final state, this is where we want to go. And then we have the system dynamics. And our goal is to find a sequence of the controls that we need to command to the motors to move the robot in a specific way from the initial state to the final state, okay? So that's pretty much what we have to do. And this is where we can add some constraints, but I'll go into a bit more detail on that as well. There are multiple methods which we can use for solving these kind of trajectory optimization problems. But today, for the purpose of this talk, I'm going to be describing direct transcription, which is my personal favorite. And the reason for that is that it's very simple, and I'm pretty sure that every one of you will understand this and will be able to go home, and if you want, you can implement this yourself. The philosophy of direct transcription is to discretize everything. So let's consider this plot here where you have time on the horizontal axis, and x is the state of the robot. So this is a multidimensional axis. Discretize everything, so we start by splitting the trajectory, the duration of the trajectory into different time segments. And at the beginning of each segment, we are going to represent the joint positions and the joint velocities of the robot at the beginning of that time segment. Okay, so those are the blue dots in the plot over there. In addition to this, we are also going to represent the torques and the forces that we are going to command to the robot at the beginning of each time step, okay? And so now you notice that there's some blue lines coming out of these blue dots. And the reason for that is that we can now get, with this information, like at each time slice, we get an idea of how the system evolves over time. So again, from those torques, for each joint position and velocity at the beginning of the time slice, we can apply them. And according to the equations of motions, we can get the joint accelerations back. And then using your favorite integration method, you can integrate those accelerations to check how the state evolves over time. Does that make sense? Okay. You can also notice that, however, the plot doesn't look right. Like there's these massive gaps and discontinuities. And the reason for that is that we're not really sure what the trajectory looks like in the first place. That's why we're solving the trajectory optimization problem. I mean, the initial values for what the trajectory may be, we can say that they're all zeros or they're all random. Or we may have an educated guess, but it will look something like that. It will not make sense. And so what we want to do is we want to be able to quantify these things called the defects. We want to be able to calculate the values of how far off we are. And if we are able to quantify those, we can pass them, we can formulate a nonlinear equality constraint to the solver saying that they must equal to 0, right? And then after a few iterations, the solver will do its magic and it should eliminate those defects by tuning the correct values for the positions and the velocities over time, and it will lead to like a fully connected trajectory. And oftentimes we just like discretize it more finely so we get a better representation of the trajectory. And so you end up with this beautifully smooth and connected trajectory. It doesn't have to always be smooth, by the way. But that's it. Pretty simple, right? So this is a summary of the whole thing. We divide time into segments, and then the decision variables in our optimization problem, they are the joint positions, velocities, torques, and contact forces for all the points that we have discretized. And then the constraints are the system dynamics. And by the way, I'm using a package in Julia that considers the full order system dynamics. So this will reason about the masses and inertias of every single link on the robot, which is really nice. A bit more computationally expensive, but it will be worth it. I'll show you why. And so the constraints are the system dynamics, just to make sure that the robot moves like a robot. The contact forces is like, so if my foot is off the ground, it cannot experience any contact forces. That makes sense. But if it's touching the ground, then there needs to be a contact force from that interaction. And then there's also a constraint on where that force is pointing. There's a concept called a friction cone. And essentially, if the force is pointing outside the boundaries of this friction cone, it basically means that the object is sliding. And so we don't want the feet to slip, so we need to enforce constraints for that. And then there's other task requirements, like if I want to grab this bottle, my end effector must be here, and if I want to take a few steps, then I have constraints on where my feet should be. Once we have transcribed all of these constraints into something that can be digested by nonlinear solvers, we can formulate high-level problems, and then have trajectories that look something like this. So this is the quadruped, and it's going to jump forward. It's a 3D visualization of the trajectory. You can see in yellow the contact forces, and in green the paths for the end effector. The paths were not encoded whatsoever. These like emerged out of the constraints that I formulated. And so maybe just, again, you can see other things like the projection at the center of mass. But essentially what has happened here is that I said the feet must be here at the beginning, the feet must be there at the end of the trajectory. In between, there's an interval in time in which the feet are not constrained to a specific place, but there cannot be any contact forces. And so the solver figures out that the only way to do this is by jumping. And then there's like also this nice video of the humanoid. It's 90 kilos and all electric motors. So it's a very small jump, not at all like Boston Dynamics, but I'm still nonetheless very proud of this jump. And you can see the beautiful behavior, like what I was referring to about like using the full system dynamics. The initial guess for this problem was the humanoid just standing still, like repeated, like the joint positions were the robot standing still for every point in time. And nonetheless, you can see that the solver finds like this nice arm motion, like to generate momentum to jump. And these were not at all encoded in the constraints. This is an emerging behavior. Okay, I'm running out of time, so I'll try to be very quick. Julia packages for robotics. These are amazing packages, and I have a lot to thank to the Julia community for having these ready and available for us to use. IPOpt and Nitro are the wrappers to off-the-shelf nonlinear programming solvers. Rigid biodynamics are for the algorithms that take care of kinematics and dynamics of complex mechanisms. Sparsity detection, forward diff, and sparsity if tools. Like these constraints are very sparse. It's basically, if you think about the dynamics constraints, the Jacobian is like block diagonal, very sparse, and each block is also sparse on its own. So it's very important to use this so we get every bit of performance we can. Static arrays for non-allocating arrays. MeshCAD for the visualization, robot operating system for interfacing with the rest of ROS, and then revise so we can update functions. Revise is amazing. I'm pretty sure you know that. Demo, and fingers crossed because live demos never work, right? So I'm going to show you a demo of Tora.jl, which is a library that I wrote for optimizing trajectories for robots for robot arms. The reason why I wrote it is I wanted to give something back to the community, but I was too ashamed of the spaghetti code that I wrote for like my research prototype code. And so I decided to start small by just doing the library for robot arms. And essentially it takes why is it not showing? I'm not sure why. Okay, I had to stop the presentation. So these are the documentation. It takes the robot model. URDF is like a very well-known format in robotics. It takes a high-level problem description, and then essentially it takes care of everything that I've just told you about. It takes care about converting these high-level problem descriptions into the mathematical constraints and cost functions that the solvers can take, and then it digests that and outputs a robot trajectory. So let's quickly go through them before the questions. I already ran it beforehand, so it should work. And you can see here that essentially what we're doing here on the Jupyter notebook, I'm loading this cell is loading the 3D visualizer, and then on this line I'm loading the robot arm. Is called the white robot arm you see there is called Panda from a company called Franca, and then we are creating a high-level problem description using Tora for this robot. And we're going to discretize the trajectory into 201 points. That's the number you see there. Maybe I can make it a bit zoom in. And then we're going to use a frequency of 100 hertz. And so essentially, if you use 100 hertz and 201 points, you obtain a trajectory of 2 seconds. And now we are going to start adding constraints. And for example, if I want the robot to start from a standstill and then the trajectory at a standstill, this is the kind of high-level constraint that I was talking to you about. We can just say, fix the joint velocities for this problem, for this robot, at the first point of the trajectory, at the last point of the trajectory, and I want them to be all zeros, okay? And then this for loop is basically saying, I want the hand of the robot to trace out a circle in space. And then the next thing we do, and the dynamics are already by default enabled, so you don't have to worry about that. Then this bit is defining the initial values to the problem, and you can see that, can we see that? Maybe I need to refresh this. Oh, you already saw the spoiler of the motion. Damn it. Well, you can see there, these joint positions, the ones currently being shown, are the ones that are repeated for every point of the trajectory. That's our initial guess, even though we want to trace a circle. It doesn't make sense. It doesn't have to. The solver will handle it for us. The velocities and the torques, our initial guess is just going to be all zeros. We don't care. It will just work. Then on the next cell, I have a bunch of options for the solver to make it work like faster, but if you use the default ones, it works reasonably well as well. We just call solve. So if I call solve, you can see that it takes 10 iterations. This is, again, a single thread and using the full order system dynamics. And it takes around, like, if I run it a bunch of times, you can see 150 milliseconds. Sometimes it takes less, depends on the weather, I guess. Now we can play the trajectory, and you can see that it's very nice, it's very smooth, and you can see that if we were just planning a motion with respect to the kinematics, so just the positions and the velocities, with the initial guess that we use, it would probably look very robotic. Like it would just like snap the configuration into each target. But you can see, however, there's a very smooth way, where, like in the way the wrist moves. And this is because we are using the full system dynamics in the constraints. And I think it looks really cool. And then we can also plot, again, the positions over time for each joint, the velocities, the torques, and then this is like the feasibility error over the iterations. So that's pretty much it. So live demos can work. Thank you, thank you. Just to finish off, like I know that there has been other people talking at JuliaCon in other Julia conferences, so I just wanted to put them here. The work that Robin and Tuan have done is really amazing, so do check that out on YouTube. And they focus more on the controls. Today I focused more on the planning, and I know there's also a lot of activity in Julia Robotics about the perception, so do check that out if you're interested in robotics. And with that, I would like to thank you all for your attention, and I will be taking any questions.
What do you think? Sorry. The next step.
Oh, okay. Is this one working as well? Okay. There you go.
What would you say are the next steps for this project and going forward for you are for the next year or so?
This was my work when I was working in academia. Yeah.
Yeah. So you're not continuing that?
I mean, I sometimes still work on it, but I have like very little time in my free time to work on it. But yeah, so I don't have like any big plans. But on my free time, I sometimes like improve the performance or add additional features to the library. Yeah.
I saw that you mentioned you are using sparse diff tools and you're creating the NLP model that you pass to ipop.jl, right?
Yes.
So basically, like, how do you? Okay, I see. I wasn't aware of sparsity direction.jl, so I was actually going to ask, how do you get out the sparsity structures, basically?
Yes. So if you the code is online, so you can check that on GitHub. But essentially, for every function that I use in the optimization problem, either for constraints or for the objective, I first pass it like some dummy inputs to get some dummy outputs, and then I use I calculate the sparsity of that, and then I use forward diff to in place get the values of the sparse automatic differentiation of those functions.
And just for an estimate, like how many parameters do you have in these optimization problems?
Okay, I think, I don't know by heart because it keeps changing. But for example, this one, again, it was, the summary it's here is like 2 seconds, 201 knots, and a few constraints, like the dynamics constraints and everything. You can see that this problem is like number of non-zeros in equality constraints, like 34,000. The number of variables are 4,200. But, you know, it works as well. If we increase this by an order of magnitude, I do hope it works. So now we are saying it's going to be, again, 2 seconds, but we are going to use 2,001 knots, and we are going to use 1,000 hertz. So this is like a very fine discretization. And if I run that again, it will take a bit longer. So instead of 10, it took 14 iterations, and 1 second for 100 milliseconds. And you can see that now everything also increased by roughly an order of magnitude. So now this optimization problem has 42,000 decision variables, 28,000 equality constraints, 3,000 inequality constraints. Like they are pretty big problems, and especially this is for a simple robot arm. But when the optimization problems for robots with legs, where you have the contact forces, they can get pretty big.
Okay.
Thank you for a nice question.
Hi. Amazing talk. Thank you very much. So I had a question as well, just in general with the Julia Robotics ecosystem.
Maybe can you speak a bit? Yeah.
Yeah. Sorry. Things like, so you use, for example, ROS to, I guess, use Julia with these robots. Things like ROS2 are not yet supported in Julia very well, or you know, moving forward, you've used rigid body dynamics, but things like, you know, other robotic simulators like Majoko aren't supported in Julia very well. Can you give any comment, I guess, in the field? Do you know of anyone working on those kind of things, or if there's any development within the Julia Robotics ecosystem?
Yeah, so unfortunately, Rob and Antoine they don't have so much time to work on the Julia packages that I've mentioned, because they're now working at Boston Dynamics. And there's a lot of work on the perception thing. I think I'm not so familiar with those packages, but I think it's Caesar.jl. So for localization, I think they're doing SLAM. For the demo that I showed in the beginning of the talk, that was using ROS1, so Robot OS.jl took care of the interface. For ROS2, I'm not working on it. I don't know if anyone is working on the wrapper for that. And about Mujoko, what was the question again? Sorry?
Just other simulators like Majoko.
I think there's an old interface for Mujoko, but it's a bit old. Yeah. And okay. Okay, I'm really sorry. I'm already over time. So thank you very much, and let's give it some room for the next speaker. Thank you very much.
Check. Hello. Hi, everyone. Thank you for attending this talk. My name is Montes Nares. I'm a PhD student at the University of Colorado Boulder. And along with my collaborator, Jie-Chi Shao, we have written a package for trajectory optimization in function space. So in the field of controls engineering, we are interested in dynamical systems. So these are things that have equations that govern them that generally take this form, like x dot equals f of x u. So some states that evolve in time and some external inputs that we can interact with the system. And specifically, we want to ask questions of optimization on these systems, such as how can a racing bike corner the fastest? Or how can a satellite, for example, adjust its trajectory or its orbit using the least amount of fuel? And questions of optimization like this are called optimal controls problems. And their solutions essentially affect every single walk of our lives. So it's very valuable to be able to answer them. Let's take a bit of a more formal look at this problem first, though. So the objective is to minimize a cost functional h, which operates on x and u, a pair of state and input spaces, which are continuous functions of time. And then f, l, and m are functions defining the dynamics and the stage cost and a terminal cost for the problem. Now, this optimal controls problem is generally hard to solve because it is constrained onto the trajectory manifold of the system, which is generally defined by nonlinear dynamics, or can often be defined by nonlinear dynamics. So this trajectory manifold is defined as the subspace of these state and input spaces, x and u. And any given trajectory, c, which is a pair of these two functions, can be said to belong to the trajectory manifold if it obeys the dynamics of the system and the initial condition. So we can rewrite this same problem with a slightly different notation, kind of grouping these x and u's into a trajectory like so. Now, the standard approach would be to discretize this problem and transcribe it as a nonlinear program, but doing so makes essentially a fundamental trade-off between the accuracy of the solution and the computational cost required to reach it, because we are approximating this trajectory manifold. When in reality, the manifold itself is precisely the search space for the solution to our optimal controls problem. So what if we didn't have to make this trade-off? What if we didn't have to do any sort of discretization at all and could instead solve this problem directly in the Banach space in which it lives, so an infinite dimensional function space? And Pronto is the projection operator-based Newton's method for trajectory optimization. It is an algorithm created by Professor John Hauser in the early 2000s, and it solves this optimal controls problem directly in the infinite dimensional function space. So as such, it does not rely on any sort of discretization of the dynamics and is particularly well suited for solving large problems that need a particularly accurate solution and fairly complex dynamics, or in the face of fairly complex dynamics. However, this algorithm is fairly mathematically complex and is generally difficult to use without having the right skill set to operate it. So our goal was to implement a version of Pronto that made this tool available to make this tool available to a broader research community. And so Julia was a particularly attractive choice for this. Given by the fact that I'm here, we use Julia for many reasons, including automatic code generation and all of the different tools that can make setting up this problem easier. But also for actually solving the problem, we have access to some of the best-in-class ODE solvers. And also the general code that you get when you write in Julia tends to be fairly transparent and provide some insights into potentially actual mathematics of what's going on in this algorithm for people to continue developing and contributing to it in the future. So an overview of how the Pronto algorithm works. Step one, we design a projection operator that can take arbitrary state and input curves and map them onto the trajectory manifold that we are interested in. Then we calculate a local search direction, again in this function space, which we do by essentially solving a reduced optimization problem on a tangent space to the current trajectory iterate. And then we determine, kind of dial in the step size by a backtracking line search, and then use the result of this, essentially the combination of the step size, the search direction, and the projection operator to take projection back onto the manifold and use that as our next iterate. So in a bit more detail, designing the projection operator. The objective of this is to be able to explore beyond this trajectory manifold for the sake of actually iterating through the problem. So this operator would need to map, or essentially be able to convert our constrained optimal controls problem into an unconstrained one. So going from something that is constrained to the trajectory manifold to something that is not. And this operator would have to be able to map things from the state and input space onto the trajectory manifold. So say you have a curve C that is a trajectory or a curve eta that is not. This projection operator would potentially look something like this. Basically, take the inputs of the input space and just plug them directly into the dynamics that you already have. This would essentially simulate the system with a different input, and you could guarantee that the result of this, the input and state pair that you would get, would in fact be a valid trajectory because you've attached all of the constraints that make it one. But this isn't particularly useful because it pretty much throws out all of the information of the state that is stored within eta. So we augment this with a regulator. Essentially just turn this into a closed loop control problem. And this then lets us also pretty accurately track the state that we're interested in, but essentially convert this arbitrary curve into a valid trajectory. So to do this, common approach is to use LQR. We can just essentially solve the Riccati equation backwards in time from a terminal condition, which is usually defined by an algebraic Riccati equation. And we do this with using Jacobians. The fx and fu that you see in there are the Jacobians of the dynamics evaluated around the curve eta. So yeah, this is a pretty useful approach. And then by solving this, we have now an operator that we can use. So the next step after this is to determine the search direction. This is done by solving a reduced order optimization problem in a tangent space to the current trajectory. And so this first step of doing so is to just take a look at the tangent space itself. So this is also defined with a linearization of the dynamics. And now with this, we want to find a search direction that will take the cost of the next step. So if we take our current trajectory and our search direction and add them together, that should be addition, it should be lower than the cost of our current step. So to find this, we can take a second order approximation of this difference. And this is done by Taylor series expansion, but using Frechet derivatives, because we're doing everything with functionals. And then the search direction will be the minimizer to solving this, this problem. Now, if we take this form, we can step through all of the different chain rules and derivatives and essentially expand this thing out to look something like this. And this is a linear quadratic optimal controls problem, which is something that in the field of controls we know how to solve analytically. First, solve a series of Riccati equations backwards in time from some terminal conditions, which gives an optimizer of sorts. And then we can use this information and solve back forwards in time to propagate that along the tangent space. And that gives the search direction. Essentially, with a reduced order representation of the system, locally sort of speaking, in which space do we have to step down this infinite dimensional manifold in order to reduce our cost. So, however, since we're solving a reduced order problem, we don't necessarily know if the step size that we took quite lines up with the actual manifold itself. So we want to be able to essentially dial it in a little bit and step back along that search direction to see whether or not we can essentially find a cost on the actual trajectory manifold that has a reduced cost from our previous step. So we do so by augmenting everything with this value of gamma. And then doing a backtracking line search, essentially along this search direction, using costs evaluated after applying the projection operator until we satisfy an Armijo condition and essentially get our step size. So once we have that step size and the search direction and a projection operator valid for our current trajectory iterate, we can combine those to then take the next step. basically travel in the search direction, the correct distance, and then project back onto the manifold to get the next trajectory iterate. So the actual algorithm itself gets fairly mathematically involved. There's several papers I'd be happy to point to if you want to know the details. So, but a quick summary, design a projection operator, find a search direction, adjust the step size, and then update the trajectory iterate. So with all of that said, the challenge of implementing this in really any language at all is being able to take a problem that's defined by a couple of functions or functionals that the user might be, or that someone solving the problem would be interested in actually thinking about, like things that define either the dynamics of and the behavior of our system, or things that we prescribe in order to design an optimal controller according to a certain set of rules that we're interested in. But taking those things and translating them into a series of differential equations that are vector or matrix valued that have to be solved alternatingly forwards and backwards in time over and over in a loop. And to solve them, you also have to take Jacobians and Hessians of these original functions that you're actually interested in and evaluate them along a trajectory, all in the process of solving these differential equations. So that in and of itself is complicated. But furthermore, so when we implemented this, we were able to just plug everything into differential equations.jl, and that was great. However, we're not able to just pass ODE solutions around in a loop because differential equations uses lazy evaluation to represent its solutions, which is a very efficient thing to do if you're only interested in solving a problem once and then using or taking a look at that solution. But chaining these things together slowly leads to an ever-growing, essentially, call evaluation chain that gets very, very expensive to compute with increasing steps. So we had to slightly modify the actual solution representation from differential equations in order to basically force some interpolations and break that chain occasionally. But fundamentally, the challenge of this is making this friendly, making this, wrapping this in some sort of interface that is accessible yet performant. And so to show you how we did that, let's consider sort of a toy problem in nonlinear controls, which is stabilizing an inverted pendulum. So let's say we want to take a pendulum and steer it to a state where it's perfectly balanced vertically. So the first thing that we would do using Pronto.jl is define a new subtype of the model type. This directly in its type definition encodes the size of the model, so the size of the states and the size of the input space. And we can also plug in any sort of parameters that we're interested in using, so that gives us the ability to explore parameterizations of the model when we're done. However, the most important thing of defining a struct like this is that that also then lets Pronto internally dispatch using the type of the model to essentially achieve polymorphism on that massive equations I showed on the other slide. So once we do that, we can encode the dynamics, and here I use a pretty trivial stage and terminal cost. If you're doing this on a real problem and we're doing real controls engineering, you'd obviously spend a lot of time thinking about these things. Q and R are some regulator matrices for the LQR for the projection operator. So this is what defining the problem looks like in Pronto.jl. And the next thing that happens is a code generation step. So it's important to note something like this is not a function, but it defines a symbolic expression that Pronto can manipulate. It uses the information from the type definition to essentially generate a palette of available symbols that we expect Pronto to have. So you can sort of conveniently use the parameters that you attach to your type. It just makes defining the problem a lot cleaner. But then this thing is traced symbolically, passed into symbolics.jl, differentiated, or potentially for some of the things we actually do some symbolic simplifications and symbolic algebra, and then we generate the customized versions or customized methods for our inverse pendulum that essentially plug into the dispatch or the method table for Pronto. So what that generated code looks like, so this is just for the actual dynamics function that Pronto would use. We basically spit out 3 different functions. One that does the memory, essentially management for numeric types, one for symbolics, and one for that actually does the proper computation in place. And we follow this sort of similar pattern from just that one definition for all of the Jacobians and Hessians of this system. So you can imagine doing something like this, which is a requirement for using Pronto, gets very, very labor intensive for much larger systems or systems that have some less friendly dynamics. And so this in and of itself is a very valuable time-saving tool. Pronto ultimately needs about 20 functions to be defined, or functions to be generated, and those get populated when you do this. So the next step is to actually run the model. So you first instantiate an instance of the actual inverse pendulum type. Since we did it with the keyword arguments, you can also modify any of the parameters that you want in there. Define a time window, some initial conditions, and then generate a guess trajectory. So the smooth function is something that we defined that basically draws a smooth line between 2 endpoints and then applies the projection operator so that we can actually feed a valid trajectory into Pronto to start the algorithm. So let's say we use a particularly bad guess, essentially, for our trajectory. So just set the trajectory to the final value that we want, which isn't even a valid trajectory of the system. Running that through the projection operator would map it onto a valid trajectory, but one that is maybe not something that we'd actually want our pendulum to do unless you have a particularly torquey motor on your system. So passing this into Pronto, and lets us optimize it, which looks something like this. And there we go. I would like to take a quick moment to acknowledge probably the greatest package ever written, which is unicodeplots.jl. Since we were representing our solutions in kind of a custom wrapper object, we were able to map just the Julia show method to generate a plot of our solution, which we found was 1,000 times more intuitive than just staring at the stream of numbers that it spit out. So yeah, let's talk about performance. So this here is a state-to-state transfer of a 2-level system. Up above is the Schrodinger equation that describes it, and the control objective for this would be to essentially steer this system from its 0 state to its 1 state. And there's a quick comparison of a couple of different algorithms here. So we compared 3 different implementations of Pronto. We have one that was originally written in C++ that used Simulink to solve the ODEs, one that was written in pure MATLAB, and then our Pronto.jl. We compared it against Koratov.jl, which is basically a state-of-the-art algorithm used to solve quantum optimal controls problems. So here you see on the bottom is the number of iterations that each algorithm took, and the y-axis is the descent. So you can see Pronto, all 3 implementations of Pronto achieve quadratic convergence and can solve this problem in 4 iterations instead of, I believe, 18. However, also, it does it quite quickly. You would expect, we would have expected a quadratic step to essentially be more expensive to solve, but that might not necessarily be the case. So, and the fact that we were able to actually, we were originally hoping to write this in a way that was easier to use first and perform it second. We ended up getting both, which is awesome. But that said, if we take a look at a profile trace of this thing, we have plenty of optimization potential still left in this package. there are some things that I'm doing that I should do differently. And so, yeah, it's exciting to see where this could potentially go. Yeah, so some applications. Pronto in the past, over the past 20 years, has been applied to everything from motorcycle dynamics to underwater vehicles to satellite trajectory optimization. But now Pronto JL has recently been applied to quantum systems. So one example that I'd like to share, one project that I'd like to share is shaken lattice interferometry. So our collaborators over in the CU Physics department set up this experiment actually on hardware where, like, let's say we want to build an atom-based accelerometer. The way that this would have to be done is by taking a Bose-Einstein condensate, shining a couple of lasers on it, one to measure the system, one to actually cool prepare the Bose-Einstein condensate, and then one laser lattice that could potentially control it. And our objective would be to design a control, or was to design a control sequence that would let us actually do the shaken lattice interferometry. And here are the results. So at the top, you see the control sequence generated by Pronto JL. And at the bottom, you see the actual experimental results from the physics lab. Both evolve over time. So on that bottom one, you essentially can see like slices in time. And what it shows is, so the top is just a pulse sequence. The bottom is shows the density of a cloud of atoms. So the first step of the sequence is to split this cloud from a single starting point to two separated clouds. Then the middle takes this, reflects the position of those two clouds against each other, and then the third portion of the sequence brings them back together. And what's particularly exciting is that a result like this has never been demonstrated experimentally. This is, as far as we know, the first time anyone's actually been able to achieve this result in the lab. And so we were able to achieve our objective, which was to make Pronto accessible to researchers doing real experimental work in the field. So we're very excited to see where else it might potentially go. And there's plenty of work still left to do. I talked about code optimization. Reduction in compile times is definitely something to think about because we're generating a lot of functions. So we can't leverage some of the tools that are available for that. We want to explore sparsity, addition of constraints, proper true variable time steps, and then potential integrations with any number of things in the Julia ecosystem. Finally, there's automatic differentiation to consider versus symbolics as kind of the driving engine for this thing. So I would like to take a moment to thank our team and our collaborators and open up the floor to any questions. Maybe I have one question.
Hey, thank you very much for the nice talk, and I love the uniplots used in the terminal, and also the comparison that you've drawn from your method compared like to discretizing everything, which is quite appropriate. You know, I guess my question is about that. If you take the approach of discretizing everything and then just passing that to using an off-the-shelf nonlinear solver to formulate your optimal control problems, then if things like joint positions, velocities, and torques are your decision variables, it becomes very easy to define constraints on the state and the control. So you can just like say, I want to have a linear inequality, an upper bound and lower bound on my minimum and maximum torque that the system is able to produce. How does it work on this approach?
So that's a great question, and thank you. The answer is it doesn't work yet. We're about halfway through implementing this, though. The way that we intend to do it is essentially attaching a whole bunch of constraints is this one? Yeah, okay, sorry. So attaching a bunch of constraints is essentially the same as modifying the cost function. So since we're doing all of this symbolic generation, what we intend to do is take our symbolically defined constraints and use them to augment the constraint equations. What you can then do is you can essentially attach a weight to those constraints and first run the solver without any constraints and then iterate through in kind of a super loop around the solver that would dial that parameter, those parameters.
Like a bi-level optimization problem, where the inner loop would, where the outer loop would ensure that the constraints would be satisfied, and the inner loop is just running your current problem.
It's more like you solve the problem assuming that you don't have the constraints, and then you slowly increase their relative weight in the cost function up from 0.
Okay.
And you use the result of the unconstrained or the optimization problem solved without those constraints as the initial guess for resolving it with more weight on the constraints.
Makes sense. Thank you very much.
Thank you. I don't believe we have time for another question, unfortunately, unless someone will. Oh wait, is this the last talk?
I think there may be time for one more question.
Then there should be plenty of time for questions. All right, fire away. Do you want to go to the picture and then come back and I'll answer any of your questions? Make sure to ask my question after the picture.
Pretty cool. It made a lot of sense to me, but it also
Yes, so that is gross. Yes. Gross yeah, I have the picture from okay. Because actually
And so, yeah, basically it's set in variable time step representation and can interpolate it in a smart way. Yeah. That's just what we use. And so what we found is like you can force it to sample to a certain time step. And that starts to affect the tolerance.
Yeah, that makes sense. So just like
he switched out the mics. We ran into the problems initially with the lavaliers, where there was some sort of weird sound, and he was having problems with the cord. He swapped the lavalier out, and then basically ended up swapping the cord out, and then we switched to the handhelds. And the handhelds were clear on the way out, but he did end up switching out like one of the XLRs. And then everything seemed to kind of stay normal. It was the power something just, I mean, the rooms are just kill yourself. It's one of those things that these rooms have something embedded in them, and just something that just doesn't work.
So that static that you're hearing today was, was the short in the mixer, but it could have just been power was overloaded, so there was like more victim to it. That's why I switched out the mixer. But that might have also been what was affecting the like RF power, something like that.
Oh, yeah.
Or maybe something weird with power. But you guys didn't run into DHCP issues yesterday?
No. No. Well, on negative there, the signal dropped like 3 or 4 times.
I think we might have. Not in maybe this room, but I'm trying to think. In 141, definitely a handful of laptops.
Some of the rooms have a way to disable it built in. It's on the panel. That's why I ran up there when we were troubleshooting that. That can't disable.
Yeah, one of these, like I have an HDMI capture card that in a pinch can sometimes find out, like.
Is it through?
I think so.
Yeah, scale it.
But this splitter works great. So this is what they have in 26, right? And these. HDMI splitter. Yeah, HDMI splitter. Of course, they get feed from.
Oh, 26
Yeah. Yeah, I think we try and use those. I mean, especially for using our long HDMI, right? Power.
That's why I carry on everywhere. They're stupid, but like they solve a lot of problems.
Yeah. We're also having a lot of them that are like starting to ship today, so it's probably cheap to have one.
Yeah, $50.
Yeah.
They're gonna fall apart. It's not a big deal. But I mean, yeah, when they go in the fritz and you're in the field.
Yeah. Alright, cool. You guys don't know where to be. Yes.
Smoke, you can disagree.
Yeah. Oh, yeah. That's another thing I'm not to worry about. There is no provided one. To the west. I think that they're having a cafe.
Oh, are they?
Yeah. Wow. So out of all the gear I could have grabbed, I grabbed a bad mixer and a bad dual.
So that's what I'm saying. I don't think so. I think there might be some weird power.
Okay, so maybe, yeah.
Because like,
yeah, well, it could also be power in this room because like these outlets right here, none of those work. That's what I originally was plugged into, and it wasn't getting any power, so I had to go over there. So it's very possible that these outlets.
I'm willing to believe that this is because so that like the RF overload. I don't know. I have no idea what that problem is.
Yeah,
and I don't know. It's possible that the receiver is just overpowered.
Right.
But like it should be regulated. It should have a regulator for that stuff. I don't know. But then the other thing is on that Mackie, I was getting channel shorts. So we were hearing was moving on.
That's what it. Yes. Okay, so that's what I was hearing.
I mean, like those Mackies are junk, but like, that generally happens when you're overloading those.
Okay, gotcha. Because I thought it sounded like something wrong with the cable, because sometimes if there's a short in the cable or something and you run a finger along it. Because that's why I was confused, because I checked for that, I reseated all my cables, and I just couldn't figure out. Because someone would be speaking and then it would drop down and you could still hear them like faintly, and then it would and go back up to full volume again.
So it's still fluid.
Yeah.
That's a good power thing.
Yeah.
I guess we do.
Yes.
Good luck.
Right. Yeah, because that floor box is working. So you see red light on that detector. So it's just at least this one. That one's working. Yeah. Who knows how often we can system these rooms?
I know.
Yes.
Next to them never unless something's burning.
Yeah.
Maybe that. As long as it goes out.
How's this room been besides the shorts?
There was that, and then there's the HTTP problem.
Where was it? It wasn't showing the slides?
Yeah.
Yes, it did that yesterday.
Oh, did it? Okay.
Yeah.
How did you fix it yesterday?
Kevin did something. Originally, the solution was Wes was doing a wide shot of the podium,
what happens with HDCP? If you ever run into this, this is what it is 100 times out of 100.
Okay.
It will show, you plug it in, it will show, you'll be like, cool.
Yes.
It'll be 3 to 5 seconds, and then it goes black.
Yep.
That's HDCP.
That's right. Okay.
So if that ever happens, you need a way to strip HDCP. HDCP is a anti-piracy thing that should never have been allowed to be created.
Right.
But it basically encodes a digital signal that just kills it. If it is not an HDCP compatible device. It's complicated. But the solution is you strip HDCP. Some of the panels, you'll see a button that says HDCP, and you want that off.
Okay, is that in the help section or in laptop presentation?
It's in different places. Sometimes it's on projector, sometimes
TechStage or something.
Right.
Yeah. Okay.
Just look for that button and see that HDCP is disabled. Okay. And then if there's not, most of these splitters will just incidentally they happen to strip HDCP. So gotcha. That's one of the things right there. Okay.
That's good to know because I didn't know that. Okay, so it's basically the HDMI equivalent of what's that terrible RC software that you put in games? Denovo?
Oh, I don't know.
There's one of those that's just basically just malware.
Yeah. I mean, for a while there was a trend of anti-piracy stuff that required root access to your computer.
Yes, I think that might be Denovo or whatever the name is. I think it might be that.
That's absurd. That was even allowed to happen for a minute.
Yeah. Well, because I think originally whatever they put into Valorant was accessing.
Oh yeah. Okay. So yes, I remember that happening. I remember everybody losing their minds about it. Did that get removed? Did they concede that?
I think it must have if people were either it did or you had a couple people online be like, oh, does she not that bad because of this? And people were like, oh,
it's that bad. Yeah. So that wasn't anti-piracy as far as I know. That was their anti-cheat.
Yeah.
Because that was part of the development of Valorant was they were gonna have the best anti-cheat.
Yeah.
And then it came out and everybody's like, yeah, if you give root access to your computer, and we could have done that the whole time, but that's not a thing that you want to do.
Yeah.
No.
Yes.
Is Valorant right? I don't think I knew that.
Yeah.
Huh.
Interesting. Yes, the first foray.
I played it for a minute.
Yeah, I've heard.
Valorant?
Yeah.
It's cool. I mean, I played Counter-Strike a lot in high school, and this is kind of they took Overwatch and made it not a stupid party game, and made it an actual competitive game. Yeah. And I was like, I'll give it a shot, and I played it for a while, and I was like, this is actually incredible, but I have no interest in playing Counter-Strike ever again. So I'm good.
Yeah. Did you say you used to do it?
I mean, not professionally, but I played on a Cal team.
Yeah.
We didn't ever win any money. We weren't that good, but we were in the circuit.
That's cool. Yes, so
Is it still active? Is that still what they're doing?
They use
roll
it.
it back.
So it looks like they took it out of June Journal. They must have taken. Let me see what the orange was. Yeah, they must have taken it out. Oh, right then. Base energy system uses kernel level driver.
Does it currently still? Like, does that mean that everybody playing League has a anti-piracy or anti-cheat system with kernel level access? That's fucked.
There's one thing saying it has low level access to the system, just like common move, but I don't. That's just a random. Yes. And apparently there's still hackers in the games. It's not doing its job. Yeah, I can't find anything like super recent about it. These are like older articles.
I wonder if they're doing that for their other games. They just have
their league.
Yeah, I know. But they have a bunch of new single player games, right? There's that like RPG thing. They have like a turn-based RPG thing.
Oh yeah.
And they're about to release a fighting game. Which like do you know anything about the fighting game community?
No. Well, yes.
They are super good. And they're actually, a lot of them are really excited about it.
That's good.
That community thinks it's going to be really good.
Gotcha.
Which is funny, because that's like you managed to impress those nerds.
Yeah. I know, yeah, I basically my only experience in fighting games was like trying out and playing through Injustice, the first one, and being like, oh wow, you like really have to input your commands really.
Yeah.
I have not like experience with this, and then I started trying to play Injustice 2 like hand-to-hand combat. Totally loved it. And it was one of those things where I was like, okay, I feel like I sort of understand this, and then I get into like even a basic multiplayer game, just be like, oh, I don't.
Oh, that's
I
insane.
just instantly get.
Yeah, it's like a weird. There's nothing else to really like. I don't play those because of this. Like, because it's one of those like unless you've been playing fighting games since you were a child.
Yeah.
You don't get to play basically.
Yep. Yes, exactly.
Like the skill ramp is just ridiculous.
Yeah. Yeah, it's one of those things where like you understand the mechanics, and then you're watching someone play, and if it's someone doing a commentary on YouTube, you're like, okay, probably gonna do like a low and I'm like, how? But obviously it's a thing of like knowing the meta, knowing what most people do, knowing what the moves are. Right?
Well, so there's this like meta of like the way that like conventions that fighting games are based on, and they all know that stuff.
Right.
So like there's these like universal terms that they have. They have their own language.
Yes.
Like I don't know why, but I kind of started watching commentators. Just because it's so interesting how dialed in everything is.
Yeah.
Like there's like I can now like it's a different language and I now speak it basically. Think of all these like EXDPs, right? Or like EX Dragon Punch. So Dragon Punch is its own whole thing. Or like Fireball is the term for any projectile. Then they've got like DI, direct input. They've got all of these like.
Gotcha.
Yeah.
That's very fun.
They're very serious.
Yeah.
They're big controversy. Have you heard anything about bots? That's one that's kind of left for that.
No.
So like they all play with these fight stick things.
Yeah.
Right. Like they like it's like it sits on your lap.
Yes.
Right.
Yes.
They all play with this.
Yeah.
It's a stick. And you whatever you want.
Yeah.
Maybe it's the other way around. I don't know. I think it's probably left-handed the stick.
interested to see, to really follow like things as they come out. It's usually been like after they've been out for a while, so it's interesting to see the new one come back, like how that. Yeah, there's a new one coming out. They're calling it more Combat 1 because everyone's
They've already rebooted the system. I guess that was like now 5 or 6 years ago.
Yeah.
When was X? That's the last one I played actually.
Okay. But yeah, basically they're doing that.
Cool.
Did you hear about the characters that they're adding part of like that?
Oh yeah, it's Homelander.
Yep.
Yes,
and then John Cena's piece.
Oh, okay.
Yeah, it's just John Cena.
It's just John Cena's best, yeah.
Yeah, and then I think a couple characters more on that, but yeah, I was like, okay, I'll be fun.
And when somebody pointed out to me that the target demographic for Mortal Kombat's like special characters that they're adding is like everybody's like 50-year-old dad. So it's like, huh?
Yeah,
it's kind of true.
Yeah. Yeah, it's true. RoboCop, Terminator, Joker. Yeah. Rambo.
Rambo.
Yeah. It's cringe.
Not for the kids.
Mortal Kombat X was amazing.
That's insane. I love how he's the first person.
No, I 29. It's been. I guess they do one like every 4. Yeah.
He was really into Mortal Kombat. John played X. It was fun. X is the one that really was right? Whatever the one with Cyber Sub-Zero.
Yes.
Yeah. That was a full reboot of the game.
Yeah, so
and that was fun. But
I know
and then Binge went too far. Like, I don't care about SEC.
Oh, yeah. And also,
so the FGC is all about Street Fighter. They like kind of laugh about Mortal Kombat.
Yeah,
they're extremely very serious. But yeah, I like to watch Street Fighter now. I don't think it's as cool. Like I really like the Mortal Kombat universe more.
Yeah. Yeah, it's always fun to look at the dual use because Or like, I don't know, I put sensors in my rack to control
Twitch plays Elden Ring.
Yeah.
Did you see the goldfish?
Yes, that's what I'm thinking of.
Yeah. Was it? Okay.
Yeah. Because it was the goldfish versus that really tough boss from a lot of millennia.
Yeah. I didn't finish it. It's really good.
Yeah. I think I got to this duo. It was one of the ones where it's like you fought this person before, and it's just very frustrating.
Yeah. I got to the big guy fighting the tiny.
Yeah.
That was the end.
That was a cool fight.
Yeah, for sure.
So
it's just like so strange.
Yes.
I didn't like what I do like. Did you play Honda?
I had played a little bit, but never enough to be already.
Do you like understand the thing about Hollow Knight and why it's like everything just out?
No.
So the concept is I just have to relate them.
Yeah.
The whole point is that there's like they make it really evident that they just made a ton of content and it's not any logical order or
Yes.
So they try to give you this feeling of like genuine exploration.
Gotcha.
Yeah. You can just go and do stuff and it always feels as relevant. It doesn't ever feel like there's like a main thing with side stuff.
Yeah, that's
Right. Yeah. It feels like everything you're doing is just it feels like there's totally endless that you can experience. And I always thought that was really cool. And I think super fast.
Yes.
But there is like right. But there's just like so much to go and do.
Yeah.
That like
How do you remember? Yeah, it was fun to try and use it. So my first roomie and I played through a camp. I got like too far and I just like, oh my god, this is so much more. So I created Megabyte and I just only got the holds as the only thing. Megabyte is
oh yeah,
Yes. Yeah, so I made Megabyte and it's also intelligence. So I had no else. And so using that, I was like, okay, I think I remember there's a stack over here. So I just like take the board and this model. So I'm classifying those two items like this. So it's like I feel like the whole game do that with darkness.
yeah, so if you software, I started with it and my initial thought was, I guess I never thought about this, but so I started with software and then I cheated it and
no, I mean, the idea is
I'm not doing this. And so I started off with SciMLCon, which apparently doesn't everybody calls it.
Yeah.
And then I don't really know what percent was
because your kind of segments that is not our disease. Yes. So it works magic. It works really well because nowadays there's like some system understanding of like aspects. They think it's the fastest speed. Like people just come up with just one for all software uses that. But it's one of those cases where they're using IOR just using the networks that are else to get it once here is insane amount of time. Then really just but yeah, so it's a thing where you basically have to do each fight either hitless or like one hit so that it gets your health.
So you intentionally take one.
Yeah. And then you have to but you just like pair through things out. But it's one of those things where you have to know.
Is there another speed running community? Okay. What are the goals? Is there
now I know the one of the fastest time is using one of the like the most insane glitches I know.
Oh, it's gonna be like less than 5 minutes, right?
There was one. I think the one that's like official was like 7 minutes or something.
Right.
Which is the fastest time in any from software.
Right, but that's like using the criteria of rolling credits, right? So
yes. Yeah.
So it's like some.
Yeah. Yeah. It's as someone doesn't understand quite what the glitch is doing, it's basically blocking and then walking forward and teleports you like 1,000 miles an hour and you skip through happening.
Right.
This is one of those things watching, you're like, how did you? There's probably distortion too. He's like a popular Dark Souls speedrunner. Yeah. He found like a lot of the weird skips in games. But he found in Dark Souls 2, there's a well that you can't access until later in the game because either need the ladder or you need it. I'm using. Because essentially, Dark Souls 1 and Remastered, in case you ever got stuck, if some weird way in the game didn't know what to do, the devs had handpicked a place that you respawn.
Okay.
But so it essentially exploits that, where it's doing like a switch, so you're using the animation of one spell, but casting this other spell. And so essentially you're teleporting to the last bonfire you rested at, but you're resting at a bonfire at the same time. And so it glitches out the game and sends you to a random location. And so you use that to like skip half the game. Because for some reason this point that they picked is on like sends you to the end game. Yeah. Yeah. But it's really difficult to do because essentially like jump at this angle, land on this canister. Time your inputs like a frame apart. And I can do it sometimes, but I cannot do it consistently.
That's what keeps me like, I feel like it's funny and interesting, but I'm not interested in respecting how.
Yeah.
The only one I've ever considered is Hades. Because there's nobody's ever found any glitches or anything to exploit.
Yeah,
it's like just get good at Hades.
Yes.
Like speedrunning Hades is just being good at Hades.
Yes.
So that I've considered.
Yeah, maybe now that I've actually like finished the first story, I'll actually watch the video. Because I remember there was like devs react towards like I see it was like a 20-minute speed run just from like a fresh game.
Yeah.
It's not. Yeah, I can see.
Yeah, the speedrun times aren't that crazy compared to like another one. Sure. Like nobody's really optimized it because there's no way to skip through like on that. You have to go. You have to visit all the rooms. You have to clear all the bad guys, and nobody's figured out like a way to do glitches. The glitchiest thing nobody's ever figured out. Yeah. Saves about a second and a half, and it's on the barge, the lumber barge. Yeah. You can dash through the door. After you clear the room.
Yeah, you just dash. Oh, right, so you don't have to wait for the animation.
That's it. Yeah. That's the only one that I can think of that anybody's ever found, is that you can like dash through a door and save a second and a half.
Yeah.
After you clear the room.
That's it.
Yeah. It's very impressive, like how well the game is made that you can't cheat it.
Yeah.
You just have to cheat it.
Yeah, well, because I think like a lot of the glitches come from devs making like, oh, no one will ever see this, so it doesn't matter that I haven't coded a wall here, because why would someone be here?
Right.
Because I think a lot of the, honestly, with speed runs, a lot of the skips you can do in Dark Souls 1, I think some of the patch remastered, is like glitching out of bounds, because there are certain areas where they didn't expect you to get. If you jump right here, you can get there, and then once you're past there, you have control over everything because they didn't code anything.
Yeah, it's called an out of bounds.
Yeah, exactly. Yeah, because I guess with Hades, I don't, you have to try nothing outside of, there's nothing for you out of bounds.
Right. Like, they specifically coded the doors, but like, that isn't the important thing. It's like, it plays an animation of you leaving the door. Yeah. So like, there's an animation that you can start until you finish the level.
Yeah. Yeah, and going, like, I think the edge of the map is probably just an image. Like, probably the only thing that is coded is the actual map data.
Yeah, right. There's no out of bounds figure.
Yeah.
I've never seen this.
Yeah. Could be a little bit.
I guess. But I mean, it doesn't have a patch no more.
That's true.
I don't think that anything's changed.
Yeah.
And there's a lot of people, I'm sure, are looking for them.
Yeah. People just spend hours and hours. I remember seeing a story about someone who, like, back in the old God of War days, like, showed up on the forums and was like, yeah, this is my time. And people were like, no, it's not possible. There's no way you can get that. Like, you're clearly cheating. And he, like, just showed them, and then, like, never showed up in the community again.
Oh.
And he just basically had some, like, bizarre glitch that he found that just, like, changed the game.
Yeah. Now, one of the biggest, it's either Mario 64 or Mario Kart 64, which those are two of the most popular speedruns, I guess. I think Mario 64 is kind of number one, right? Or like maybe Mario Brothers, for instance.
Yeah.
Most popular.
Yeah.
But those ones are still he stored a speed run basically. So he was number one,
yeah.
and then he waited for somebody to spend months and months beating him.
Oh, yes.
And then when they did, he just drops the video he's been sitting on until somebody.
That's very funny.
So somebody took his spot.
Yeah.
For like 12 hours or something
Yeah.
like that, and then he like.
That's the pettiness
I
that I
know,
live
right?
for.
And it's probably like all of that, like that story that
Yeah.
people are like telling him.
Yeah.
Like that represents like 100th of a second in a video game.
Yes. Yeah.
That's how ridiculous
Yeah.
that community is.
Yeah. I know. Really, trying to think of, I've seen, I've been watching, or Steph's been watching all the speedruns of Only Up. It's basically like, basically one of those games where you're just jumping on objects and going higher and higher.
Like the
big
crazy
one.
the what?
What was it, the person who's in like a pot?
Yeah,
big axe.
the hammer. What's it
Yeah.
called?
I don't remember what that one's called.
I don't remember, but it's like a crazy. It's like a.
Yes.
It's like a. What's the painter? Not Goya. I don't remember. Basically, there's this Renaissance painter who painted like absurd apocalyptic weirdo shit,
yeah.
and that's what inspired that game.
Yeah. Yeah, this one Only Up is essentially just like a 3D version of that. Where you're just jumping on items. But it's one of the ones where like
a 3D platform.
Yeah, and then you'll be falling for a tiny bit, and I think eventually if you fall like long enough, it just puts an invisible wall, and it just sends you like there's basically a point where you can catch yourself maybe, and then after that it's like you just watch yourself fall. Yeah. So we were watching some of the speedruns, and there's a few times where someone just like missed time to jump, and they did something weird, and you're just sitting there watching them.
Does it soft block your game? And you have to like.
No, you can start over again. It's basically just like if you're doing this speedrun, you've lost so much time.
Get over it.
Yes, that's what it was. Yeah, I was trying to explain that to someone, and I was like, I don't remember the name. Like,
Are there co-op speedruns?
Probably.
I don't know if there's an end to co-op though.
Oh, yeah.
Because that makes me like.
It's always funny because I'll check out like speedruns of games like the Lego games, and sometimes there will be some like glitch they found, but sometimes it'll just be like, it's just like, oh yeah, there is a co-op.
Oh, okay. They set distance.
Yes. 45 seconds.
45 seconds to go 100 meters.
I love that the difference between first and second place is 100 milliseconds. Someone finished one 18 days ago, about to sixth place. That's like, that's the most recent.
Interesting. I don't think this is. I think this is just completely optimized. There's no glitch or anything. He's just like. I think they've just perfectly figured out how to like have a foot on the ground to that for as little time as possible. This is the number one.
Yeah. I think it's hilarious that they have splits.
Oh yeah, he's doing splits for.
That's very fun.
Okay, so they just ignore the hurdles. It's one of the clock speedrun. Kind of looks like a person on it.
Yes.
I would have expected him to at least be upside down.
Yeah.
What time do we start back up?
2, I think. So yeah, I might run out. There's so much. Yeah, well, yesterday I think it kind of like thinned out about this time, but I'll stick my head out and see.
We move the chairs so they stop
plenty of chairs, but just go sit down.
They all want to sneak in and kind of sneak out.
Yeah.
Lines aren't too bad. Most people have already grabbed stuff, so.
Did you power these off?
No, I did not.
Somebody else did.
It's very nice, all nice.
Okay, I think it's time to get started. I'm Morten. I'll be the chair of for the following 2 hours. We're going to start off with a birds of a feather session. So won't actually be a talk. This will be an interactive session, and I think Joris expects people to chat along. But yeah, so Joris is the technical team lead for the JuliaSim application product. So he has, I think, a lot of opinions on how to build applications in Julia. So go, take it away.
Yeah, then we'll just do it without the mic. Can I just turn it off?
But my idea about it is here, like it's been a really good time keeping it back. Yeah, I mean it's normal. I'm doing higher than you did it. I'm new though with coming. I'm just doing like so I'm getting to meet like the first time.
Okay. Okay. Yeah. Now we're back to normal talks for the next hour. And first up, it's Oscar Lavreni. He's a postdoc in Belgium in UC Leuven.
Yeah.
And
you pronounced it correctly.
Sorry?
You pronounced it correctly.
Perfect. Yeah. I have a little bit of French training, so. Yeah, so his research interests are in high-dimensional statistics and dependence modeling, but you're actually an actuary by training, so we'll be talking about Copula.jl. Thank you.
I have a half hour to talk to you about Copula.jl, which is an attempt that I made a year and a half ago now to implement in Julia a set of useful tools for statisticians, which are Copulas. So the talk will be a little theoretical on the start. I'm going to give you a thorough introduction of what are Copulas, why are these things useful. And then we are going to talk a little about the implementations. I'll give you a few use cases that are already working, and I'll also give you a few glimpses of what's the future of the current implementation. So, a copula is simply defined as the distribution function of a random vector that has uniform margins. So it's a random vector in dimension d, which is supported in the unit hypercube, and its marginals are uniform. And in fact, there is this theorem from Sklar, which says that for any random vector x, if you write fx, the distribution function of the random vector itself, and fxi, the distribution functions of the marginals, then there exists a function c, which is unique once the random vector is absolutely continuous, that gives you these functional equations between fx and the fi's. Yeah, the notation is not the same on the top and the bottom, but yeah, you'll follow. This existence and uniqueness of the copula gives you a way to separate the problem of estimation of the distribution of the random vector into, on one side, the estimation of the marginals, and on the other side, the estimation of the dependent structure, which is the copula. This separation can be useful for a lot of stuff. You might have more information on the marginals than the copula. It might be the other way around. It's less common, but and also you might be able to construct a lot of parametric structures from parametric copulas and parametric marginals that are not from the same classes, and it gives you a freedom of modeling that is larger than what we have if we only consider multivariate parametric models. So a few comments. I just said that is that the function C describes and contains the dependent structure apart from its marginal distributions. And I have a few examples. The first one is the function pi, which is simply the product function. And this gives you a random vector which has independent marginals. And the two other ones are called Fréchet-Hövding bounds. And this is actually the minimum possible copula that you can have and the maximum possible copula that you can have, pointwise. They represent full, complete comonotonicity between the marginals and full negative dependence between the marginals. And as for univariate distributions, of course, there are a lot of families, of parametric families that are known, and we are going to discuss a few ones right now. The first one is the family of elliptical copulas. This family is easily described by using the concept of spherical and elliptical random vectors. And we say that a random vector X is spherical if multiplying it by an orthogonal matrix keeps the distributions the same. Yeah. And then a linear transformation of this vector is elliptical. This is in fact the case for Gaussian random vectors. This is also the case for other random vector than Gaussians. You can think about students, for example. And then the elliptical copula is simply derived from these random vectors by applying the scalar theorem that we just saw on the previous slide. So there are two main used family, the Gaussian and the student. But there is also the possibility in the package to provide your own elliptical generator and to do the same thing with another family. If you see that if you have a positive and univariate distribution, by making it turn around the center of the plane, you can construct a spherical random vector, and then from it you can extract the dependent structure. This is an example of a sample from a bivariate copula, the Gaussian one. With quite a high sigma, and so it's a sample on the unit plane, the unit square, and you see that there are more points in two of the corners, which means that the dependence is quite positive. When one of the random variable will be big, the other one will be big too. Yeah. Another class of copulas that is how to put it. Central in a lot of stuff that happens in finance, for example, is the class of Archimedean copulas. To define them, I first need to define the property of a function to be d-monotone. And we say that a function phi is d-monotone if it has at least d-2 derivatives, and the sign of the derivatives alternate. And the last one is non-increasing and convex, which means that the sign of the d-1 and d derivative also alternate, even if they don't exist. A function that has this property for all d, for example, will be called completely monotone, and these are functions that are really smooth. Like if you take, for example, exponential minus t, that's a function that is completely monotone. From this function, we defined Archimedean generators, which are d-monotone functions that are normalized to be 1 at 0 and to go to 0 at infinity. And then the function that is described as, and there should be a -1 somewhere, C of u equals phi of sum of the phi -1 of ui's. There is a -1 missing. This function is actually a copula. It's a distribution function which has uniform marginals when phi is an Archimedean generator. This parametrization gives the dependent structure that is completely symmetric. You see that the sum gives everything, gives every dimension the same weight. So that's one important characteristic of those dependent structure. But also the parameter of the model is now a function. So we have a freedom that is a little bigger than, for example, with a Gaussian model where the only parameter is a matrix. So there are some classical parametric families of generators. The first one is e to the -t, which generates the independent copula, the independent scopula. There is also the Clayton, the Gamble, the Frank, the Ali-Michael-Heil, I think it's the name of the third one. I don't remember. And there is a lot of them. There is a paper from Nelson in 2006 that gives a very comprehensive list with more than 30 of them. Of notable generators that are used and that corresponds to model that people actually use by time to time. Okay. Those copulas are a lot less easy to sample than the Gaussian ones, right? To sample the Gaussian ones, you simply sample a Gaussian random vector, and then you apply the normal CDF, the normal inverse CDF to get back to the normal quantile function to get back to the unit square. Here it's a little more complicated, and in fact we have some decompositions that allow to sample them correctly, which is called the radial simplex decompositions. There is also another one that I will discuss a little less, which is called the frailty representation. And what it says is that the vector u that is following an Archimedean copula with generator phi can be decomposed. So the dots are exactly the broadcasting from Julia that you'll expect into phi of a product between a uniformly distributed random vector on the simplex That's a random vector that will give you the direction in which the point will go in the space. And then R is a non-negative random variable that will give you how far it will go in the space, which should be independent from S. And in fact, there is a transformation that is called the Williamson transformation that gives you a mapping, a bijective mapping between the function phi and the distribution of the random variable R. And so from the generator phi, if you can compute this mapping, you can obtain the distribution of the random variable R, and then you can sample it, sample uniformly from the samplex independently, and then multiply the two, apply phi, and you get a sample from the Archimedean copula. There is also another representation which is used by the OR package, but which I don't use, which simply constructs not OR, but 1 over OR, which has phi as its Laplace transform. So it's not exactly the same transformation, but it might also be useful. The problem is that this one is only working when the generator is completely monotonous and not demonotonous, which is a kind of a restriction. And there is also on the bottom of the slide a few references for these representations. So here you have 2 examples. On the left, that's bivariate Clayton. You can see that the bottom of the graph is very dependent, and so the left side of the distributions will have a high dependency, but the right of the graph is a lot less dependent, and so the right side of the distributions will be independent asymptotically. And on the right, it's a Gumbel model in which it's kind of the other way around. You also see that the shape of the structure is not exactly the same. There is also the possibility to construct empirical copulas from data sets. And it's actually quite easy. You just need to take the ranks and then renormalize them correctly to obtain something that lives on the unit hypercube. And this application here that constructs the U's from the ranks of each marginals just renormalized gives you, if you take the empirical cumulative distribution function of U, that's the empirical copula of the x's. The problem with that is that this model is usually not a copula. It doesn't have uniform marginals. It's a discrete stuff. And so there are a lot of smoothings that exist in the literature. For example, there is the Bernstein smoothing, there is the beta smoothing, there is the checkerboard smoothing, and all of them can be useful and are implemented and can be used directly through this empirical copula stuff. Where you can pass it the x's or the u's as you want, and say that you want it to compute the ranks or not. So yeah, let's try to talk a little more about the implementation. In the package, we have a thing that is called the sklardist and the function fit that allows to do stuff like what's on the blackboard. I just load the packages. I defined the distribution for the marginals. I define C as being a given copula. And then the sklardist constructs the vector D that is just applying the Sklar theorem, which has as a dependent structure the copula C and as marginals x1, x2, x3. I can then sample it like you'll sample anything from distribution.jl. It's a proper continuous random vector from distribution.jl. You can also fit it directly by passing to the fit function the type that you obtain. So it's just sklardist of the name of the copula and a tuple containing the name of the marginals. And then you pass it the data and it will fit it. Here the copula is not the right one. The marginals are the right one, so the fit might be really bad, but it's working. And we actually comply with what distributions.jl said in its documentation, which is that the fit function will choose a reasonable way to fit the distribution, which in most cases it's maximum likelihood estimation. So here, what we do is that we use the fit function from the marginals from distributions.jl, and then on the residuals from those fit function, we use whatever we want to fit the copula. For the Gaussian and the elliptical ones, it's actually maximum likelihood. But for the Archimedean one, it could be maximum likelihood, but for the moment, it's a moment a moment matching algorithm that runs in the background. So this is practical. This is something that is on par with what is available in the OR package, which I kind of translated into Julia to obtain this kind of behavior. About this translation, here is the actual implementation of the Clayton copula in the package. It's just a few lines. And then the infrastructure around it to define the Archimedean copula is not that big either. And if you want to define your own Archimedean copula, it's actually quite simple, right? You just need to tell it what's the generator, the inverse of the generator, what's the tau. I did not describe it, but it's a dependence measure, the Kendall tau, the inverse of the Kendall tau, and then you need to give it the radial distribution, the distribution of OR. The equivalent in the OR package is hundreds, thousands of lines of codes, right? The API for the Archimedean stuff is moreover quite modular in the sense that from these functions here, you are not obligated to provide everything. If you provide only phi and phi inverse, you will be able to compute the CDF, the density, and a lot of stuff. If you provide only the radial dist, you will be able to sample from the distribution. And what else? Yeah, and that's what I was saying earlier. If you want to fit it, you need to provide the inverse tau because that's what I'm currently using to fit it. But actually, if we implemented correctly the Williamson transform, which I didn't do yet, you could even fit it through maximum likelihood by just providing phi and phi inverse. Yeah. So even if you don't do much, if you don't know much about the Archimedean family that you want to use, it's still possible to do stuff and to leverage the architecture that is already here to fit it correctly, to sample from it, blah, blah, blah. So I have a few usage examples that are directly coming from the fact that we hook into distributions.jl infrastructure. And the first one is that Turing works straight out of the box without doing anything, which is kind of spectacular because to do those kind of stuff in OR, it's a pain. Here I just have a Turing model with a few pre-errors for some parameters. There were more in the model that I used, but the screen is not big enough to put too much stuff, so I reduced it to a bivariate model. And then there is the distributions of the marginals. We define the copula. We define the scalar distributions, and we just call Turing.addLogProb to add the log likelihood of the model. And even the log likelihood function is not one that I programmed myself. The log likelihood function is coming from distributions.jl. I had nothing to do to make it work. This is possible to fit a model in a Bayesian context. So you'll get samples of the parameters, and you get uncertainties and stuff. But it is also possible to fit models that are more complicated in Turing, for example, regression models, where the residuals are following, while the residuals might not be just standard Gaussian, they might have some dependent structure that you fix beforehand into one of the parametric families, and then Turing works its way and finds the right parameters. This is something that is impossible to do in OR, and here it's free. Another example that I really like is called global sensitivity.jl. It's not mine, it's just that those guys needed to implement some things called Shapley effects, which are a way to model the influence of the inputs of a black box model onto the output of this model. A little better than what Sobol effect might do. Sobol effects is the Gaussian version, and Shapley effects are the version with a dependent structure. And so they just hooked into Copula.jl and implemented their stuff. And if you look at the documentation, I did not put the code on the screen because it's a little long, but it's actually a pretty nice piece of code. There is also this one, which was a little less expected. And there is this guy called Alec that from Julia Actuary that actually used copulas to correlate Black-Scholes models when he samples some stocks, and to avoid using several stocks that are independent from each other, which is an hypothesis that is probably completely wrong. He had this thing called correlated, where you just pass the stocks and you pass the dependent structure that you want, and it produces stocks that are correlated, which residuals are correlated with these dependent structures, of course. This is also something that is hard to do in other languages. Yeah. I don't know why it says "or the future" here. Yeah, I'm starting to arrive to the end of my slides. There is potentials for other integrations with the current state of the field. The one that I really like is probability bounds analysis. It's a package that assumes the fact that you don't know the dependent structure between your random stuff, and it will give you bounds on, for example, the sum or the maximum or stuff like that, assuming that you don't know how the things are correlated with each other. And it's a pity because they came before Copula.jl existed, and they actually re-implemented a lot of stuff. Well, I re-implemented a lot of stuff that I already had. And we have a plan. There is a pull request to remove this duplication and actually use the Copula.jl stuff. And there is also fuzzylogic.jl. 3 days ago, I stumbled upon this guy called Luca at the registration desk, and he told me about this fuzzy logic stuff. And fuzzy logic is a field where you replace the AND function on the standard logic by what you call a T-norm, which is a fuzzy AND. And in fact, copulas are T-norms. And we took a look, and in fact, it will be possible, and we plan to do in the next few days or months maybe to hook into Copula.jl so that you can use the parametric models that we have to produce fuzzy logic T-norms. There are probably others. If you have some, I'm all ears, of course. And there is also some potential for future developments of the package. This is things that I don't really have the time to do right now, but which I am supposed to do. The documentation is not comprehensive enough, of course. It's never. There is a lot of models that I want to add. The hierarchical Archimedean copulas, the Vine constructions might be really nice to have too. And there is also some kind of dependence metrics that I did not define, that I did not talk about here, which might be interesting to add to the package. And yeah, there is also the problem of estimators, because those models are maybe harder to estimate than what we already have with the maximum likelihood and the moment matching stuff. Of course, if you find some missing functionality, do not hesitate to come to me. Voilà, thank you very much for taking the time to listen to me, and if you have questions, I'm all yours.
Okay, yeah, for the questions, I'll pass on the microphone to you.
So I know you mentioned fitting, using it to fit data into a Copula. Do you also have ways to simulate, let's say, simulate a Copula based off of parameters?
Yeah, we got two. We got the rand function from distribution.jl that works, and that samples from the Copula, or from the star distribution. It's the same thing. You can put a C instead of the D in the rand function. It works. That's for sampling, and for fitting, we simply hook to the fit function from distribution.jl. Yeah.
Also, is it type stable?
Yes.
Okay.
I bet so. I hope so. Yeah, for the moment, it looks like it's type stable. Yeah.
I have a question. Have you tested it with the high-dimensional copulas?
I can't hear you.
Can you hear me?
Yeah, it's
okay.
better.
I'm wondering how your package performs with very high-dimensional copulas, like 50-dimensional, 100-dimensional, because
even with the simplest independence copula, if you multiply 50 numbers between 0 and 1, you get numerically 0. So have you tested that?
Yeah, that's actually a very good question. It depends on the model. For the elliptical ones, the fact that the dimension is big is not very a problem because we use what's already available for high-dimensional Gaussians and high-dimensional students into distributions of the GL, so it works quite correctly. For the Archimedean ones, for the moment, I had no issues with that. There is this algorithm to sample the density. I think I've not to sample the density to compute the density of the model. You actually need to derive this function phi d times, d being the dimension, and this derivation can be done in the R package. It was done by hand until d equals 8, and then you're fucked. But what we did here is that we used forward diff, and forward diff can actually go pretty far. Yeah, so I pushed it to 20, 50 I did not try. But the thing is that for higher dimensions, usually you don't use those copulas directly. And for higher dimensions, what you want to do, if I can't find it, is actually Vine's copula, which is a way to imbricate the copulas, the one with each other, and so you only have to define and to use bivariate models to construct something that can be high-dimensional. But this is not implemented yet, right?
Around having to multiply that many by okay. In R, they get around having to multiply numbers that are very small by computing the log CDF or something like that. So yeah,
yeah.
So
yeah,
okay.
Turing computes the log of the density. The thing computes the log of the density, not the density itself, of course. Because it doesn't work.
Why doesn't it work?
I don't know. It's a very good question. There is actually, no, that's not, no, I'm sorry. There is a discourse thread that's not on the thing that discusses that with the people from Turing. But yeah, if you have a good idea for what it doesn't work, then...
It seems on the face of it, it should work.
Yeah, but it doesn't.
Okay.
I don't know why.
What was the question that you just answered?
Oh, the question was why I'm using adlock prob and not directly the tilde from Turing.
Oh.
And the answer is that because it doesn't work, and I don't know why.
Do we have any more questions? I'll try to get to you. Oh, can we pass the mic back?
My question is about the definition of the Archimedean copula. So I guess that this is an important definition because it allows you to, I guess if you have an Archimedean copula, you know that it's going to be simpler to sample or estimate. What do we gain by knowing that a copula is Archimedean? And it seems to be quite an important definition.
Yeah, so first of all, the definition is wrong. This should be phi minus 1 and not phi. This one here should be phi minus 1. Why it's an important class? It's because the function C is a function from 0, 1 to the D into 0, 1. So you have a big space, which is 0, 1 to the D, in which you need to do stuff. And here we reduced that onto the estimation of a univariate function. And this reduction is interesting because you may be able to use information from all the dimensions to compute this univariate function, right? And so, yeah, that's why the class is so used in the literature.
Okay, I think that's all we have time for. So let's
thank you very
Oscar
much.
Again. Okay, and next up, which I think is the last talk of this stream, will be from Nesrine Wallace. She is a renewable energy engineer from Humboldt University in Germany. And we're going to hear about joint chance constraint optimization.
Yeah, thanks a lot. So let me. Okay, so I'll present to you today some applied stuff, how to apply joint chance constraints for, in the case of economic dispatch in power system applications. So my talk will be quite applied and not much into into the mathematics behind the things, but this will show you where Julia can be used in real life, out there in real life programs. So I'm Nesrine. I am an engineer in renewable energies at the Humboldt University in Berlin. I present to you today the joint work with my colleagues Tatjana Grandon, who is an economist from Europe University Flensburg, and the mathematicians René Henrion and Holger Heitsch from the Weierstrass Institute. It's been quite fun doing interdisciplinary work with these people, so yeah. So first of all, I'll present to you the models that we start off with to implement this microgrid islanding concept. And then I'll present to you briefly the computational methods that are implemented in the package jcc.jl. And then I'll present you the application that motivated all of this usage of joint chance constraints, which is the microgrid islanding, and then present you also some results on what was the what was achieved on the trade-off between the costs of such powerful constraints and the robustness for this optimization under uncertainty, and then I'll conclude with some remarks. So it's a vast scope of optimization under uncertainty. What I will want to present to you here is first, where are we exactly on that big map? It's basically this minimization of an objective function given this constraints that have random vectors as an input. And of course, the applications of this are quite numerous in engineering, where we have, especially for renewable energies, for example, random meteorological data or random demands in power, water networks, or even gas networks. And also, in other aspects or other fields, such as the position of random obstacles in robotics and random demographic data and pension fund management, and so on and so forth. So this can be, I present here the case that we studied, but it could be, applied to other fields. So the common solution is to take a decision before observing the random vector, but what we want to do here is basically have some reformulation of equation number 1 such that we can consider the uncertainty of the random vectors. So typically, or one thing that is very easy to do is to use these expected values for the randomness, and this is easy to solve, and the solutions come at low cost, but it's also very not robust. This is probably very easy to everyone. There's also worst case constraints where we try to implement this for all possible distributions or all possible cases, which is absolutely robust, but extremely expensive or does not even exist. And something that's in between is chance constraints or probabilistic constraints, where we have then a probability of fulfilling the inequality meeting a certain level, which is then a robust solution, not too expensive, but it's often difficult to solve because this function phi is not explicit. But again, we have numerous applications, so this is the challenge that we want to do today, is how to implement this, also with the specificity of having that as a joint chance constraint. And I explained that on here, not yet, but just simply showing you that these general chance constraints can have several types. First type is a separable one, where we have the, which is quite common in capacity optimization in stochastic networks, or bilinear models, where we have then a multiplication of the random vector and decision vector, which comes, for example, in blending or mixture problems in chemical engineering, for example. We focus on the separable case, and further options are also that we could either have these chance constraints. When we generate the chance constraint, it can either be joint or individual chance constraints, and I explained this briefly. This is basically that we say we want the we want the inequality to hold for many points in the range, and that all of this satisfies a certain p-level reliability, whereas for individual chance constraints, these are just punctual in time, and it's not like the it's not then like covering all possible like cases. So it's where this the difference between the two. With the case, for example, if we have this random right-hand side inequality, we can simplify the individual chance constraints as such, and it becomes quite simple in the individual case where we just implement the p quantile of the random xi vector. But this model with individual chance constraints maintains deterministic simplicity, so it's quite often a strong numerical simplification. We have linear models, but it is often also the wrong model. For example, in the case of microgrid, or if we have a grid outage, then we want the microgrid to survive, or like the islanding to be successful for all possible points of that outage. So if it starts at time point 1, we want, and we know the outage is 3 hours long, we want the microgrid to survive during the whole time of an outage, and not basically in the single points in time. So the joint chance constraints allow these windows of p-level reliability instead of singular points in time, which is basically needed in power system planning. And further on, I will present to you the concept of microgrids and why this is relevant there. But also joint chance constraints lead to these nonlinear models, which increases computation complexity and cost. And so there are quite known structural properties of joint chance constraints, which I will not discuss here, but I can refer you to these many works about the continuity, differentiability, and convexity of these constraints. So the computational methods that we looked into and that we also implemented into the JCC package is, first of all, so we use this for an optimization problem, so we need to provide sufficiently precise approximations for values and gradients of the probability function. And we do this using 2 methods. The first one is by using quasi-Monte Carlo by the efficient code by Gens. And so what we do there is to analytically reduce the values of the probability functions and the gradients to values of the Gaussian distribution function. And this is quite straightforward, but we can only do this for Gaussian distributions. And another method that we implement is the spherical radial decomposition, where we have, then we use another polar coordinate system such that we can implement nonlinearities also of the nonlinearities of the constraint in the random vector, and then we also have could use this for Gaussian and Gaussian-like distributions, so it's more power, can be applied for more cases than the simple Monte Carlo code. I'll present to you now briefly what we implement in our package. So the package offers functions to compute the multivariate probability function and its gradient using the Gens algorithm. It's already implemented in the function MV normal CDF, so we have that into our in our package, and then also we define the gradients of that probability function. It computes also the multivariate probability function, its gradient using the spherical radial decomposition. And then for user friendliness, we also implemented how to, like, a function that could register the user-defined function and adds it to a jump model to complete the optimization model. So we have a preliminary version of the package that is already online. I still need to work on some things there, so it's not yet the final version, but it will be released very soon officially on GitHub and on the Julia package manager. So now I'll present to you the application of that we use this package for. and also how it's being used in a real-life microgrid in Tanzania. So the overall aim is to increase the resilience and reliability of renewable-powered microgrids. And I come to the definition of microgrids in a second, but this is increasingly relevant in cases of advanced grid infrastructure where we have high shares of renewables that are very distributed, and therefore we need to do lots of local balancing of these microgrids that are connected to a higher level grid. But it's also very relevant in cases of poor electricity access, where we have frequent main grid outages and where microgrids are usually very crucial to supplying electricity to a local community. More concretely, the goal is to ensure that the microgrid is able to autonomously serve the customers with a given P-level reliability. And we've been already discussing this with operators of microgrids in several locations about how this can be used for tariff setting regulation, so it's quite policy related, on how to what the tariff is for a certain P-level reliability. That is quite powerful information on how to regulate tariffs. So what are microgrids? They are small electrical distribution systems, usually at low voltage levels. They connect distributed sources of energy generation. So we have, for example, PV, small hydro, diesel gensets. We have dispersed storage units, and also energy loads that can be either sensitive or flexible for shedding and controllability. And microgrids can be connected to the main distribution network or operate in standalone mode, so the islanded mode. And when connected to a higher level grid or to other microgrids, this can be seen as an active distribution network contributing to overall system stability. Yet still capable of working independently in case of faults. Okay, so the challenge in the microgrid dispatch is that although grid-connected microgrids have been basically the future of energy systems in many contexts, they are quite, they're not so easy to plan or to do there are quite many challenges for the dispatch problem. I have on the left here the typical topology of such a microgrid, and that is we have always this connection to the grid, and then we have these power generation side and the power consumption side. And then we have these typical uncertainties where there are, of course, stochasticities in the renewable energy input and also stochasticities in the demand. In the cases of these unreliable higher level grids, we have then also an uncertainty about the frequency of the outages that can happen for the main grid, but also the duration of these outages. And with the model that we present, we are able to cover all of these four uncertainties using joint chance constraints, and I will demonstrate what our results were. So the main concept behind this is to, conceptually, we introduce new decision variables that are reserves that can compensate for forecast errors and main grid outages with a P-level reliability. And it has been done so far that these reserves cover the individual case, like individual chance constraints. What we do here is that we make sure it doesn't only cover the hour that an outage starts, but during the whole duration of an outage. Coming to the model formulation, so we have the typical economic dispatch formulation where we maximize an operational net profit. Then we have all sorts of box constraints, storage intertemporal constraints, energy balancing constraints. All of this describe the physical model of the microgrid. And then we add to that the probabilistic constraint that we want the so the randomness or like the errors, and also basically we want the reserves. We want the reserves denoted here as R that are for in the battery and the diesel to be always larger than the possible errors that can happen, and also the possible to compensate grid outages if they occur. All of this with a given P-level reliability that we set beforehand. So this, in this case, is the individual chance constraint case where we then define that for all possible starting points of an outage. For the joint chance constraints, we have that we need this probability to be satisfied for all time steps within the outage range, so that if it's starting at tau, then it continues until tau plus kappa, that we know we can satisfy this probability, or like we have enough reserves to cover these uncertainties with a given level of probability. And now I present to you a few of the results. So the case studies where we used this, we used real data about the sizing and the profiles from a running microgrid in Tanzania, supplying around 100 households. We use also real measurement data to get these distributions of the forecast errors that you see here for the first two types of uncertainty that we handle. And what we get is, if you see here, this is the regular the dispatch if we do not consider any chance constraints. And what we have is different dispatches from different generation components. For example, using the diesel component during the night, also some battery discharge during the when we have solar generation, we use that to charge the battery and also export to the grid. All of this to cover the black line, which is the demand that we have in the microgrid. So this, we do not yet consider any chance constraints. Now, if we introduce individual chance constraints, we have with a probability level of 90%. We have a very small change that's more battery charging is happening, a bit less grid export, which comes at a cost of losing some profit from that export that we did. And then if we do it again for joint chance constraints, then we see a lot more diesel is being deployed during the night, thus keeping in more reserves from the battery for the case of an outage. This I just wanted to show again. This can be also seen again in the battery cycling, for example, that in the regular case we have less charging than in the individual case, and in the joint case we have also less discharge during the night here and more charging during the day. So this just to showcase what the optimizer actually did with these reserves. And this is the planned reserves also that so all of this just translates into the same thing, that we have for the individual chance constraints certain reserves that are planned, and for the joint one we have more of those in terms of diesel and battery reserves. I wanted to showcase, if we take, for example, 10 simulations of the errors that could happen, and this, on the left-hand side, everything that is below 0 would then be a failure of the grid, so that all of that would be load that is just shedded and not, fulfilled. And on the right-hand side, you have, with an individual chance constraint, then at each of these time steps, if an outage happens, then it can cover it, but not if the outage, persists for a few hours. But still, we can see that with 10 simulations, we have the curve is shifted upwards, so we have less violations of that, and that is, in this case, with 10 simulations, always one curve or one possibility that is not satisfying the inequality. Comparing individual and joint chance constraints, we can see that for joint chance constraint, now we're looking at reliability windows. This is if the outage starts at time step 1. This is at, it shows them randomly 1, 8, 16, and 24. And then you can see that then it is made sure that it's not violating the probability function over the whole window, ensuring a p-level reliability window. So the example I just presented had 24 nonlinear inequality systems. It had, the decision vector had a dimension of 270, so it's not a small problem. What we had was a loss of profit of very little, 0.2% when using the individual chance constraints, and 0.5% when using joint chance constraints. And this also doesn't yet showcase the value of lost load of an actual outage. So all of those curves that were underneath 0, all of that would be basically load not met or lots of losses for the system. In terms of comparing the two computation methods for the probability functions that I presented earlier on, there were, so the spherical radial decomposition was always around 3 times slower than the Gens code, with an outage duration of 3 hours. It was in this scale of, or like in this speed. And what we did is, if we increase the number of, or like the duration of an outage, we see that the two methods converge more towards each other. Since for the Gens code, it is quite dependent on how many, what's the dimension of the multivariate probability. So if we have here a higher kappa, then it will translate also in more computational effort by the program. Just some concluding remarks. So with that last slide, we showcased that joint chance constraints achieve a good trade-off between cost and robustness for optimization under uncertainty. We were able to cover 4 different uncertainties with different types of distribution functions. And the work is still ongoing to have the release of the package with a comprehensive documentation. And also, just as a side note, the package will also be released as an autarky energy library, which is for decentralized microgrid management and planning. Which from that there hasn't been so many packages in this field. Lots of energy models in Julia are more of a large scale. Level. So in this case, we have the specific use case of decentralized microgrids. And also another promising thing is that these algorithms will be piloted in 4 different sites, among other in Tanzania and Nigeria, by in grid-connected microgrids that are run by microgrid small and medium enterprises, but also energy communities that will make use of the open source codes and the hopefully ease of use of these codes to manage their, or like increase the reliability of their electricity supply. So I have a few references, mainly about the structural properties of the probability functions, and thank you so much.
Thank you very much. Are there any questions? So I have a couple, actually. One is a very naive one. So this is like a kind of, what I saw is like it's a plugin to Jump, right, in a way, or you can plug it into Jump. So I'm not an optimization person. I know very little about Jump, but Jump is like a library of a bunch of different optimizers. So does this work with basically every optimizer, or is it something where like the optimizer has to support these types of constraints?
No, so they are. So how it's done is that these probability functions are calculated. So in Jump, there is this possibility to register user-defined functions and give the value and the gradient for that. So it's actually can be used by any nonlinear solver. There isn't any constraint on that. So.
Okay, that's very cool. Any questions? Yes.
You might have covered this, but I'm not sure. The randomness on the, say, like the resource for solar, can this model capture like time series autocorrelation kind of randomness, or only like correlation across the different variables?
I'm not sure I understand the question. If it's okay.
So you have to assume some distribution for the random vectors in this case, like the renewable resource. Is that distribution considering like independence of like from one timestamp to another, or does it consider the way that they're correlated?
It does consider the correlation between each time step, and that's the key thing for the joint case, where we have all of these time steps. Like, for example, in the case of kappa, the outage being 3 hours, then we look at the distributions of each of these 3 time steps, and there we also have the correlation between them.
Thank you for a very nice talk. Have you considered the case where you don't have diesel available? So diesel allows you to handle some of the inflexibility. Is there a case where you can perhaps scale the solar installation to be able to cover any shortfall? Have you considered scenarios like that?
We did do one run, like another case study with no diesel, and then the battery was being a lot more employed for the of course, because that would be the only slag component left. But yeah, it was considered also, and then so it can be also.
Another maybe a little bit naive question that I would have is, it was good to see like the use in like open source and have the communities themselves be able to use this optimization, right? So who is the sort of the customer of this software, I guess? Are we talking about like the energy company, or is it like the controller that's running the PV cells, something along those lines? Or where does it actually run the code in the end?
So the concrete context that we have of these pilot projects are, for example, these companies. They're privately owned companies, and they run these microgrids. There would be the one customer. That's the case of the microgrid in Tanzania. If there was also interest, for example, in Germany, which is an energy community. So the concept of that is that a group of individuals just own their energy assets, and then according to their internal structures, there's then someone that, and sometimes they outsource that type of the work of the controller, basically, and that would be, so the customer would be the energy community itself, but then someone implementing that into their smart controller for handling the dispatch. And like the idea is that these dispatches are all then algorithmically implemented, and they are kind of running always in a rolling horizon. So it's like optimizing for each day every 15 minutes. So yeah, they could implement that in that case. So it could be either the energy company or groups of citizens that have created an energy community and own their assets, which have been lots of cases of such things happening, especially on this small scale level of microgrids.
That's very cool. Do we have more questions?
You may have just kind of answered this, but it looked like a lot of this was on the hour level. Have you looked at like a smaller time scale, just given that that's important for reliability concerns?
Yeah. So we did also do this for 15 minutes. That was the smallest time scale that we looked at, and it is usually done for 15 minutes. Dispatch, to know that. Depending also on how flexible the generation assets that you are assuming you have in your microgrid. So
there might have been somewhere, but how long does it actually take to run this one optimization?
So just one, for an example, just 1 day, so 24 time steps, where in this case it was an hour and not 25. So the GANS code took 7 seconds and the SRD 20 seconds. And it's a nonlinear problem. The decision vector was 270 big. So
you could theoretically like run it every minute or something. And
yeah.
Right. If there are no more questions, then let's thank Nasreen again.
Thank you.
And I think that concludes the stream then. Thank you very much.